Welcome to the Sleepy Scientist. It's lovely to have you here. Before we set off, let me ask you something simple. Where in the world are you watching from tonight? Maybe you're tucked away under a blanket, resting in a quiet room, listening on a late walk, or half sinking into the sofa with the lights turned low. Wherever this finds you, I hope the world feels a little softer for a while. If these calm journeys through science help you relax, think, or gently drift towards sleep, then a like and subscribe is always deeply appreciated. It helps this small, sleepy corner of the internet keep moving quietly through the cosmos. And if you're already subscribed, thank you. Truly, your support makes all of this possible. Now, tonight's subject is one of those ideas that sounds simple at first, and then quietly rearranges the furniture inside your brain. So with any luck, it will be interesting enough to carry you along, but not so interesting that you suddenly sit upright at 3 a.m, wondering whether time itself has been behaving suspiciously. Although, if that does happen, at least you'll know why light is not just fast, but woven into the rules of space, time, and cause and effect. A slightly inconvenient but scientifically respectable reason to lose a little sleep. So let's begin gently. Why does reality have a speed limit? And what is the universe protecting by never letting anything outrun light? There is something quietly strange about light. It is everywhere, so familiar that it almost disappears from thought. It spills through windows in the morning, glints on water, bounces from pages, screens, mirrors, clouds, skin, dust, and distant planets. It makes the world visible without asking to be noticed. It arrives so quickly that, in ordinary life, it feels instant. A lamp is switched on, and the room is simply bright. The sun rises, and the sky is simply there. A phone screen wakes, and tiny coloured pixels are suddenly ready to tell you things you may or may not have the emotional strength to deal with before breakfast. But light is not instant. It travels. In empty space, light moves at about 300,000 kilometers per second. That is so fast that it can circle Earth more than 7 times in a single second, if it had a convenient circular path and no errands to run. It crosses the distance from the Moon to Earth in a little over 1 second. It takes about 8 minutes for sunlight to travel from the Sun to Earth, which means the daylight touching your face is already 8 minutes old by the time it arrives. Every sunny afternoon is, very gently, a message from the past. And yet, as astonishing as that speed is, the deepest mystery is not simply that light is fast. The deeper mystery is that this speed appears to be the limit, not just a limit for light, not just the top speed of a very energetic beam, not merely the performance record of the universe's fastest little messenger. The speed of light in vacuum seems to be woven into reality itself. It is the maximum speed at which information, influence, and cause and effect can travel through space-time. It is less like a speed sign beside a cosmic motorway, and more like a rule built into the road, the map, the clock, and the idea of direction all at once. That is where the question becomes much larger than light. Why should reality have a speed limit at all? In everyday life, speed feels like something that should keep increasing if enough effort is applied. Push harder, and an object moves faster. Add a stronger engine, and a vehicle accelerates more quickly. Fire a rocket for long enough, and it seems natural to imagine it could simply keep gaining speed forever. This is the common sense picture, and for ordinary motion it works beautifully. A bicycle, a train, a thrown ball, a falling stone, and a car on a motorway all behave in ways that mostly agree with this intuition. Add energy, gain speed. Add more energy, gain more speed. Nature appears to be politely straightforward, but physics has a habit of being polite only up to a point. At speeds much lower than light speed, The universe lets ordinary intuition get away with a great deal. The rules discovered by Isaac Newton describe falling objects, orbiting moons, moving carts, and swinging pendulums with extraordinary accuracy. Newtonian mechanics is not childish or wrong in any simple sense. It is one of the most successful descriptions of motion ever created. It is just not the whole story. It is the version of the story that works when speeds are gentle compared with the speed of light. When motion approaches light speed, the familiar rules begin to bend, not because the universe becomes chaotic, but because the deeper order starts to show through. Space and time no longer behave like a fixed stage on which events simply happen. They become part of the physics. Distances can be measured differently by observers in relative motion. Time can pass at different rates. Energy and momentum begin to relate in ways that are not obvious from everyday experience. The simple idea that speed can be increased without limit begins to break down. This is the world of relativity. In 1905, Albert Einstein published the special theory of relativity, and with it came one of the great changes in human understanding. The speed of light was no longer just a value to be measured with better instruments. It became a clue that space and time themselves were not what they had seemed to be. Einstein showed that if the laws of physics are the same for observers moving steadily relative to one another, and if light in vacuum is measured at the same speed by all such observers, then the universe must be arranged in a deeply unexpected way. Time is not absolute. Space is not absolute. Simultaneity is not absolute. The speed of light is. That sentence is easy to say, but it is a profound rearrangement of reality. Before relativity, it was natural to imagine that time ticked at the same universal rate everywhere, like a great invisible clock behind the cosmos. Space was imagined as a vast container, and objects moved through it. But special relativity replaced that picture with something more subtle. Space and time are linked into space-time, and motion through space-time is governed by a limit that no ordinary object can exceed. The speed of light is tied to electromagnetism, because light is an electromagnetic wave. It is tied to mass, because objects with rest mass require more and more energy as they approach that speed. It is tied to massless particles because anything without rest mass, such as a photon in vacuum, travels at that limit. It is tied to causality, because information cannot outrun it without threatening the order of cause and effect. And it is tied to space-time because the limit appears not as an optional feature of light, but as part of the geometry of the universe. This is why calling it the speed of light can be slightly misleading, though it is far too late to rename it without making every physics textbook sigh at once. Light did not win a race, and then demand naming rights. Rather, light travels at the maximum speed because it is massless, and because electromagnetic radiation follows the deepest causal structure of space-time. The limit was there in the rules. Light simply reveals it. A better phrase might be the speed of causality, or the maximum speed of information, or the universe's built-in conversion factor between space and time. None of these are quite as catchy, admittedly. The speed of light has a certain elegance. It sounds simple, even though the idea hiding behind it is anything but simple. To see why this matters, imagine a universe with no speed limit. In such a universe, signals could travel instantly. A change here could be known everywhere at once. A message could cross any distance without delay. At first, that might sound wonderfully convenient, especially for anyone who has ever watched a buffering symbol and briefly considered abandoning civilization. But a universe without a causal speed limit would be a very different place. The order of events could become unstable. The distinction between what can influence something and what cannot would blur. Relativity shows that if faster-than-light signals were possible in the ordinary sense, different observers could disagree about the order of cause and effect. In some cases, a message could appear to arrive before it was sent. That is not merely odd. It threatens the basic logic by which physical events are connected. The speed limit of reality helps preserve the structure of cause and effect. It tells the universe what can touch what can know about what, and what must wait for information to arrive. It gives the cosmos a kind of ordering principle. Not a moral order, not a human order, but a physical one. Events are not all equally connected. They sit within space-time, separated by distance and time, and only certain paths allow influence to travel between them. This means that light speed is not just about fast travel. It's about whether the universe can tell a coherent story. Every beam of starlight crossing space is carrying information at the fastest speed allowed. Every radio signal from a spacecraft, every pulse from a distant pulsar, every flicker from a galaxy billions of light years away is obeying the same rule. The universe does not update itself everywhere at once. It communicates locally, patiently, at a finite speed. Even reality, it seems, does not get instant notifications. So the strange rule beneath everything is this: there is a maximum speed, and that maximum speed is not an inconvenience added to physics. It is one of the reasons physics works at all. It connects light, matter, energy, space, time, and causality into a single framework. It explains why the night sky is a view into the past, why no rocket can simply accelerate without limit, why black holes can trap light, why distant galaxies are seen as they once were, and why cause and effect remain in an order the universe can keep. Light is fast, almost unimaginably fast, but its speed is not only a number, it is a boundary, and somehow, within that boundary, the universe becomes understandable. Before light became the universe's great speed limit, motion seemed like a much simpler affair. For a very long time, speed looked like the kind of thing that could be added, subtracted, and increased without any deep cosmic complication. If a horse carried a rider across a field, the rider moved with the horse. If the rider tossed an apple forward, the apple's motion included the motion of the horse and the extra speed of the throw. If a boat drifted down a river while someone walked along its deck, the person's speed could be understood by combining the walking speed with the motion of the boat. The world appeared to behave like a neat stack of movements placed on top of one another. This picture feels natural because it matches ordinary life. A moving train carries everything inside it along with it. A ball thrown from that train keeps the train's motion, while also gaining the motion of the throw. A child jumping in the aisle does not slam into the rear wall because the child, the air, the seats, and the train are all already moving together. Most of the time, motion is wonderfully cooperative in this way. It does not announce its deeper secrets while someone is trying to eat crisps on public transport. One of the first great steps toward understanding this was made by Galileo Galilei. In the early 17th century, Galileo described a form of what is now called the principle of relativity. He imagined being inside the cabin of a smoothly moving ship. If the ship moved steadily, without rocking or speeding up, many experiments inside the cabin would seem just the same as they would if the ship were still. Drops of water would fall normally. Small creatures would move around normally. A person below deck would not be able to tell, from simple local experiments alone, whether the ship was resting or moving uniformly. That idea was quietly powerful. It suggested that steady motion is not absolute in the simple way people might assume. Motion is measured relative to something else. A passenger may feel at rest inside a smooth carriage, while someone standing beside the road sees the carriage moving past. Neither description is useless. Each belongs to a different point of view. What matters is the relationship between observer, object, and frame of reference. Galileo's insight did not yet contain the full modern theory of relativity, but it planted an important seed. It showed that nature does not always privilege one obvious state of motion over another. If movement is smooth and unchanging, it can become almost invisible to those sharing it. Earth itself gives the grandest version of this. The planet rotates and orbits the sun at great speed, yet no one has to cling to the nearest tree each morning to avoid being swept into the shrubbery. Everything nearby shares Earth's motion, so daily life feels still. Then came Isaac Newton, whose work gave motion a mathematical structure of extraordinary power. In the late 17th century, Newton formulated his 3 laws of motion and the law of universal gravitation, creating a framework that could describe falling apples, thrown stones, tides, cannonballs, planets, moons and comets with the same underlying principles. It was a spectacular unification. The heavens and the earth were no longer separate realms governed by different rules. The same mathematics that described an object falling near the ground could help explain the moon's continual fall around Earth. Newton's first law states that an object remains at rest, or continues moving in a straight line at constant speed, unless acted upon by a net external force. This is the law of inertia. It explains why motion does not need to be constantly maintained by force, even though friction in ordinary life often makes it seem that way. A sliding object slows down because surfaces, air resistance and other forces interfere. Remove those effects and motion simply continues. Newton's second law links force, mass and acceleration. In everyday language, a stronger push produces a greater change in motion, while a more massive object resists that change more strongly. Newton's third law states that forces come in pairs. When one object pushes on another, the second pushes back with an equal and opposite force. These laws made the universe appear beautifully mechanical, like a vast clockwork system whose motions could be calculated if the positions, velocities and forces were known. At the heart of Newton's picture were absolute space and absolute time. Space was treated as a fixed stage, stretching everywhere, whether or not anything occupied it. Time was imagined as flowing evenly throughout the universe, the same for all observers, like an invisible cosmic river. 2 events that happened at the same time for one person were assumed to happen at the same time for everyone. A second here was a second there. A ruler here was a ruler there. Reality seemed to offer a stable background against which all motion could be measured. In that classical world, velocities combined in a straightforward way. If a carriage moved at one speed and a ball was thrown forward inside it, an observer on the ground could add the 2 speeds together. If the ball was thrown backward, the speeds could be subtracted. There was no obvious final boundary. With enough force, enough time, and a sufficiently determined engine that had not yet exploded from sheer ambition, it seemed an object might continue gaining speed indefinitely. And for ordinary purposes, this picture works astonishingly well. Newtonian mechanics can describe the arc of a football, the fall of rain, the swing of a pendulum, the recoil of a cannon, the motion of machinery, and the orbits of planets with remarkable accuracy. Engineers still use Newton's laws constantly because, at everyday speeds and in ordinary gravitational conditions, they are exactly the right tool. Bridges, aircraft, engines, buildings, spacecraft trajectories, and countless machines can be analysed with Newtonian ideas to an accuracy that would have seemed almost magical in earlier centuries. Even the motion of planets became understandable through Newton's law of universal gravitation. Earth orbits the Sun because the Sun's gravity continually bends Earth's path inward, while Earth's own motion keeps it from simply falling straight in. The Moon orbits Earth in a similar balance. This view transformed the night sky from a mysterious arrangement of wandering lights into a system whose motions could be predicted. It was one of the greatest achievements in the history of science. So classical physics did not fail because it was silly, primitive, or careless. It succeeded magnificently. Its apparent failure came later, when scientists began asking questions outside the range where human intuition had been trained. Newtonian mechanics was built from a world of stones, ships, planets, springs, pendulums, and falling bodies. It was not designed around particles moving close to light speed, clocks flying around Earth, or electromagnetic waves crossing empty space. That is not a weakness so much as a reminder that every theory has a domain where it speaks most clearly. The cracks appeared when physicists began to understand light more deeply. For sound to travel, there must be something to carry the vibration, such as air, water, or solid matter. For waves on a pond, there must be water. So it seemed reasonable to ask what carried light. If light was a wave, what was waving? Many scientists imagined that space must be filled with a very subtle, invisible medium called the luminiferous ether. This ether was thought to provide the background through which light waves moved, much as air provides a medium for sound. At first, this seemed sensible. Light behaved like a wave in many experiments. It could reflect, refract, interfere, and diffract. It carried energy across empty space from the sun to Earth. If waves usually needed a medium, perhaps light did too. The idea of ether allowed physicists to keep much of the classical worldview intact. Space could still be a kind of stage, and light could be a wave travelling through something hidden within that stage. But light had already begun to behave in ways that made motion less simple than before. As scientists studied electricity, magnetism, and optics, they were drawn toward a mystery that Newton's framework alone could not settle. Motion still seemed easy when it involved ships, stones, and planets. But once light entered the story, the old idea of simply adding speeds began to look less secure. If Earth moved through the ether, should light travel at different measured speeds depending on Earth's direction of motion? If a lamp moved toward an observer, should the emitted light behave like a thrown object, carrying extra speed from its source? If light needed a medium, why was that medium so strangely impossible to feel? These questions did not destroy classical physics all at once. Science rarely changes with that kind of theatrical crash, however tempting it is to imagine a chalkboard dramatically splitting in two. Instead, the questions gathered slowly. The old view remained powerful, useful, and mostly correct for the world humans could touch. But behind it, light was quietly asking for a deeper explanation. The universe still looked Newtonian from the ground, but somewhere inside the behaviour of light, the first hints of a speed limit were beginning to appear. The mystery of light became much deeper when scientists stopped treating electricity and magnetism as separate curiosities. For centuries, electricity and magnetism seemed related to familiar but different kinds of strangeness. Electricity could make sparks jump, hair rise, and amber attract small bits of dust after being rubbed. Magnetism could pull iron, guide compass needles, and make invisible forces seem to reach through empty space. A magnet did not need to touch a nail to tug at it. A charged object did not need to touch a scrap of paper to pull it closer. Something was happening in the space between things, and that something was not easy to picture. The key idea that helped change everything was the field. Michael Faraday, one of the great experimental physicists of the 19th century, developed a powerful physical intuition for electric and magnetic fields. Faraday was not trained as a traditional mathematician, but his imagination for physical processes was extraordinary. He pictured lines of force filling the space around magnets, wires, and electric charges. These lines were not just decorative drawings. They represented the idea that space itself could carry influence. A magnet was not simply reaching magically across a gap. It was surrounded by a magnetic field, and that field shaped how other objects behaved nearby. This was a quiet revolution. Instead of thinking only in terms of objects pulling or pushing across empty nothingness, Faraday encouraged physicists to think of the space around objects as active. A charge produced an electric field. A magnet produced a magnetic field. A changing magnetic situation could produce an electric effect. This was seen clearly in electromagnetic induction, where a changing magnetic field can drive an electric current in a wire. It is the principle behind generators, transformers, and much of the electrical world humming politely in the background, while everyone pretends not to depend on it every minute of the day. Faraday had the physical picture, but it was James Clerk Maxwell who gave that picture its grand mathematical form. Maxwell was a Scottish physicist whose work in the 19th century unified electricity and magnetism into a single theory called electromagnetism. Before Maxwell, scientists had discovered many separate rules describing electric charges, currents, magnets, and induction. There was Charles-Augustin de Coulomb's work on electric forces. There was André-Marie Ampere's work on currents and magnetism. There was Faraday's law of electromagnetic induction. These pieces were powerful, but they did not yet form a fully unified picture. Maxwell gathered these ideas and reshaped them into a coherent set of equations. In modern physics, they are known as Maxwell's equations. They describe how electric fields and magnetic fields are produced, how they change, and how they relate to one another. The details can be mathematically demanding, but the central idea can be stated gently. Electric and magnetic fields are not isolated actors, they are partners. A changing electric field can create a magnetic field, and a changing magnetic field can create an electric field. This is where the story becomes beautiful. If a changing electric field can produce a magnetic field, and a changing magnetic field can produce an electric field, then under the right conditions the two can sustain each other. A disturbance in the electromagnetic field can travel outward as a wave. The electric part changes, creating the magnetic part. The magnetic part changes, creating the electric part. Together they move through space as an electromagnetic wave. Maxwell calculated the speed of these waves using known electrical and magnetic constants. The result was startling. The speed came out extremely close to the measured speed of the light. That was not a small coincidence. It was one of those moments in science when two distant paths suddenly meet in the same clearing. Light, which had been studied through lenses, mirrors, prisms, colours and shadows, appeared to have the same speed as waves predicted from electricity and magnetism. Maxwell recognised the implication. Light itself was an electromagnetic wave. This changed the meaning of light. It was no longer only the stuff of vision, colour and brightness. It became part of a much larger family of electromagnetic radiation. Visible light is simply the small portion of that family that human eyes can detect. Other forms include radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays and gamma rays. They differ in wavelength and frequency, but they are all electromagnetic waves. The universe had been sending messages in the same basic language all along. Human eyes were just reading one very narrow page of the book. This also made the speed of light feel less arbitrary. Before Maxwell, one might imagine light's speed as a property belonging to light itself in a fairly ordinary way, rather like the speed of sound belongs to sound moving through air. But Maxwell's theory suggested something deeper. The speed of light emerged from the behaviour of electric and magnetic fields. It was connected to the structure of electromagnetism. It was not merely how fast a beam happened to go. It was a natural speed built into the field equations themselves. Still, this discovery also created a puzzle. Waves, in everyday experience, usually need something to wave in. Sound waves travel through air, water, or solid matter. Ocean waves travel through water. Ripples on a pond travel through the surface of the pond. So if light was a wave, many physicists assumed there must be some medium carrying it. This hypothetical medium became known as the luminiferous ether. The word luminiferous means light-bearing, which sounds rather grand, as though the universe had hired an invisible butler to carry photons across the room. The ether was imagined as a substance filling all of space. It had to be strange. It needed to be thin enough for planets to move through it without obvious resistance, yet stiff enough to carry light waves at enormous speed. It had to be everywhere, but almost impossible to detect. It had to allow Earth to move through it, while somehow leaving no ordinary trace. The more physicists thought about it, the more peculiar this invisible medium became. But at the time, the idea was reasonable. If light was a wave, and waves needed media, then light probably needed one too. Maxwell's theory had revealed light as an electromagnetic wave, but it had not yet removed the old expectation that waves must be carried by something material. The field itself was still difficult to accept as fully real. Even though Faraday and Maxwell had made fields central to physics, many scientists still wanted a mechanical picture underneath them. This is why Maxwell's achievement sits at such an important turning point. His work did not yet create special relativity, but it made relativity almost impossible to avoid. It showed that electric and magnetic fields were aspects of one unified electromagnetic reality. It revealed that light belonged to that reality, and it placed the speed of light inside the laws of electromagnetism, rather than treating it as just another measured speed among many. The old classical picture still imagined space and time as fixed, steady backgrounds. It still allowed velocities to be added in the ordinary way. But Maxwell's electromagnetic waves seemed to carry within them a specific speed, a speed that appeared in the equations themselves. That was awkward. If an observer moved toward or away from a beam of light, should the measured speed change? If Earth moved through the ether, should light travel differently depending on direction? If the speed came from the fields, what exactly were those fields doing in empty space? These questions did not yet have their final answer, but the path was narrowing. Electricity and magnetism had become electromagnetism. Light had become an electromagnetic wave, and the speed of light had begun to look less like a detail of optics and more like one of the deep numbers of nature. The universe had not yet given up the full secret. But Maxwell had found the clue glowing inside the fields. By the late 19th century, light had become both more understandable and more mysterious. James Clerk Maxwell had shown that light was an electromagnetic wave, a travelling disturbance in electric and magnetic fields. That was a magnificent discovery, but it also left physicists with a very natural question. If light was a wave, what exactly was waving? In ordinary experience, waves usually need a medium. Sound needs air, water, metal, or some other material to carry vibrations. A shout cannot travel through empty space, which is why space is famously quiet, apart from the occasional dramatic film, soundtrack taking certain artistic liberties. Ocean waves need water. Ripples need the surface of a pond. Even a wave passing through a rope needs the rope itself. So if light behaved like a wave, it seemed reasonable to assume that it too must travel through something. That imagined something was called the luminiferous ether. The word luminiferous means light-bearing, and the ether was thought to be an invisible medium filling all of space. It was not supposed to be ordinary air because light from the sun and stars crossed the apparently empty regions between worlds. It could not be a thick fluid, because planets moved through space without being slowed in any obvious way. It had to be present everywhere, yet almost impossible to feel. It had to carry light waves at enormous speed, yet offer no noticeable resistance to Earth, the Moon, or anything else drifting through the heavens. It was, in short, a very demanding substance. The ether had one job, but apparently required the strangest employment contract in physics. Still, the idea made sense within the older worldview. Physicists were used to thinking of waves as motion within a medium. Maxwell's theory had shown that light was electromagnetic, but many scientists still hoped there was some mechanical background underneath the fields, some hidden substance that made the wave possible. If the ether existed, then Earth should be moving through it as Earth orbited the Sun. And if Earth moved through the ether, that motion might be detectable. This led to one of the most famous experiments in the history of science. In 1887, Albert A. Michelson and Edward W. Morley carried out an experiment in Cleveland, Ohio, designed to detect Earth's motion through the luminiferous ether. The basic idea was beautifully careful. If Earth was travelling through an invisible ether, then light moving in different directions should be affected slightly differently. A beam of light travelling into the supposed ether wind might take a tiny bit longer than a beam travelling across it. The effect would be extremely small, but with a precise enough instrument it might be seen. Michelson and Morley used an interferometer, an instrument that splits a beam of light into two separate paths and then brings those beams back together. One beam travelled in one direction, the other travelled at a right angle to it. After bouncing between mirrors, the beams were recombined. If one beam had taken a little longer than the other, because of Earth's motion through the ether, the returning light waves would no longer line up in quite the same way. This would create a shift in the interference pattern, a delicate arrangement of bright and dark bands formed when waves overlap. The principle can be pictured without the machinery becoming too heavy. Imagine two swimmers in a river. One swims upstream and downstream, fighting the current one way and being helped by it the other. The other swims across the river and back. Even if both swimmers move at the same speed through the water, the flowing river changes how long each journey takes. Michelson and Morley were looking for something similar, but with light beams and a supposed ether wind instead of swimmers and water. Fortunately for the swimmers, they were not asked to measure 19th century optics. The expected result was a shift in the interference pattern as the apparatus was rotated. If the ether wind came from a particular direction, rotating the instrument should change which light path was more affected. The experiment was sensitive enough to search for the tiny difference. If the ether existed in the expected way, the light should have revealed Earth's motion through it. But the expected shift did not appear. The result was essentially negative. Michelson and Morley did not detect the ether wind. Light did not behave as expected if Earth was moving through a stationary luminiferous ether. The experiment didn't prove, instantly and dramatically, that the ether was impossible in every form anyone could imagine. Science is rarely that tidy. But it did show that the simplest and most expected version of the ether was in serious trouble. This became one of the most important negative results in physics. A negative result can sound disappointing, as if nature simply forgot to attend the appointment. But sometimes not finding something is exactly what changes the direction of science. The absence of the expected ether wind forced physicists to ask whether their assumptions about light, motion, space, and time were wrong in a deeper way. Several scientists tried to explain the result while keeping some form of the ether. Hendrik Lorentz developed mathematical ideas showing how moving objects might contract slightly in the direction of motion. George Fitzgerald had suggested a similar possibility. This idea became known as length contraction. If the arms of Michelson and Morley's apparatus contracted by just the right amount as it moved through the ether, then the expected timing difference might be cancelled out, hiding the ether wind from detection. This was not a foolish patch. Lorentz's work was mathematically important and helped shape the path toward modern relativity. The Lorentz transformation developed in this context, later became central to Einstein's special theory of relativity. It described how measurements of space and time change between observers moving relative to one another. But before Einstein, these ideas were often interpreted as effects happening because of motion through the ether. The ether was still being preserved, but it was becoming increasingly elusive. That was the awkward part. The ether had been introduced to make light easier to understand, but now it required a growing collection of special explanations to avoid being detected. It had to carry light, fill space, allow planets to pass through it, and hide perfectly from experiments designed to reveal it. A theory can survive complications, of course. Many good scientific theories are subtle. But when an invisible thing must become more and more carefully arranged to remain invisible, physicists tend to grow suspicious. The deeper possibility was far more radical. Perhaps light did not need a mechanical medium at all. Perhaps electromagnetic fields were not disturbances in some hidden material substance. Perhaps they were fundamental physical entities in their own right. Perhaps the speed of light did not have to be measured relative to a preferred background, because there was no preferred background. That idea was difficult to accept, because it meant giving up the comfortable picture of space as a fixed stage filled with an invisible light carrying fluid. But the failed search for ether opened the door. The Michelson-Morley experiment did not, by itself, create special relativity. It did something quieter, but extremely powerful. It removed a support beam from the old world view. It showed that the universe was not cooperating with the expectation that light moved through a detectable cosmic medium. The old picture of waves demanded something to wave in. Light, however, seemed to be telling a different story. In the end, the ether was not found. No wind blew through the apparatus. No preferred direction appeared. No hidden stream announced Earth's motion through the cosmic background. Instead, light continued to travel with a stubborn consistency that did not fit the old assumptions. The universe had offered physicists a clue shaped like an absence, and sometimes, in science, the thing that is not there is the thing that changes everything. In 1905, Albert Einstein changed the meaning of speed. That may sound a little dramatic because speed appears to be one of the simplest ideas in physics. Something moves from one place to another. Measure the distance, measure the time, divide one by the other. A person walks slowly. A train moves faster. A planet sweeps through space. A beam of light crosses a room so quickly that the journey seems to vanish. Speed feels obvious, almost too familiar to be suspicious. But Einstein looked at light and saw that the obvious picture could not be right. By the beginning of the 20th century, physics had inherited two powerful ideas that did not sit comfortably together. Newtonian mechanics described motion with extraordinary success, especially for everyday objects, planets, machines, and falling bodies. Maxwell's theory of electromagnetism described light as an electromagnetic wave travelling at a particular speed in vacuum. The trouble was that Newtonian motion seemed to allow speeds to add together in the ordinary way, while Maxwell's equations appeared to give light a fixed speed, built into the behaviour of electric and magnetic fields. Something had to give. Einstein's great move was not to treat the speed of the light as a small technical problem. He treated it as a clue about the nature of space and time themselves. In 1905, he published his paper on what became known as the special theory of relativity. The word special does not mean minor or unimportant. It means the theory applies to a special case. Observers moving at constant speed in straight lines, without acceleration or gravity being the main concern. Even within that apparently limited setting, the consequences were enormous. Special relativity rests on two central postulates. The first postulate says that the laws of physics are the same for all observers moving uniformly relative to one another. Uniform motion means steady motion in a straight line, without speeding up, slowing down, or turning. This idea reaches back to Galileo Galilei's principle of relativity. A person inside a smoothly moving ship or train should not be able to perform a simple local experiment and discover some absolute state of rest. If the motion is steady enough, the laws of mechanics behave the same way. The second postulate is the more unsettling one. The speed of light in vacuum is the same for all observers in uniform motion, regardless of how the light source or observer is moving. That is where ordinary intuition begins to wobble politely, then sit down for a moment. In daily life, speeds seem to add. If a train moves forward and someone walks forward inside it, a person standing beside the track measures the walker's speed as the train's speed plus the walking speed. If someone throws a ball from a moving vehicle, the ball's motion combines with the vehicle's motion. This seems so natural that it barely feels like a theory. It feels like common sense wearing comfortable shoes. But light refuses to behave like that. If a spaceship were moving toward you and switched on a headlamp, you might expect the light to reach you at the speed of light plus the speed of the spaceship. If the spaceship were moving away, you might expect the light to arrive more slowly. That is what ordinary velocity addition would suggest. Yet special relativity says that every observer in uniform motion measures light in vacuum moving at the same speed. Not nearly the same, not usually the same, the same. This is not because measuring devices are confused. It is not because light secretly adjusts its behaviour to be annoying, although one can understand why 19th century physicists may have felt personally targeted. The point is deeper. If the speed of light is the same for all such observers, then measurements of space and time cannot remain fixed and universal in the old Newtonian way. Einstein did not simply declare that light is fast. He showed that keeping light's speed constant forces space and time to become flexible. This is the heart of the transformation. In Newton's picture, time was absolute. It ticked at the same rate everywhere for everyone. Space was also absolute, a vast stage on which objects moved. Observers might disagree about how fast something was moving, but they were assumed to agree about lengths, durations, and whether two distant events happened at the same time. Special relativity changed that. If two observers are moving relative to each other, they can measure time differently. They can measure distances differently. Most strangely, they can disagree about simultaneity. Simultaneity means whether two events happen at the same time. In ordinary life, this seems straightforward. Either two lightning strikes occurred together, or one happened before the other. Surely that should not depend on who is watching. But in relativity, it can. Imagine two lightning strikes hitting opposite ends of a moving train. A person standing on the platform might judge the flashes to reach the midpoint between them at the same moment and conclude that the strikes were simultaneous. A person riding on the train, moving toward one flash and away from the other, may receive the light from the two strikes at different times. Once the constant speed of light is properly accounted for, the train passenger and platform observer may not agree that the strikes happened at the same time. This does not mean reality becomes imaginary or personal in a casual sense. It means simultaneity across distance is not absolute. There is no single universal now that every observer must share. Events that are separated in space can have different time orderings depending on motion, so long as they are not able to causally influence each other. This sounds strange because human life unfolds at speeds far below light speed, where the effect is too tiny to notice. The universe kindly hides the weirdness during errands. Special relativity reveals that space and time are not independent containers. They adjust together so that the speed of light remains constant. Moving clocks tick differently when compared with stationary ones. Moving lengths are measured differently along the direction of motion. Time and space trade roles more subtly than everyday experience suggests. What once looked like a simple question about how far something moves becomes a question about how reality organizes events. A few years later, Hermann Minkowski gave Einstein's ideas a powerful geometric interpretation. Minkowski had once been one of Einstein's mathematics teachers, and he recognized that special relativity could be understood more elegantly if space and time were combined into one structure: space-time. In this view, the universe is not made of three-dimensional space with time flowing separately in the background. Instead, events occupy a four-dimensional space-time, with 3 dimensions of space and 1 dimension of time woven together. Minkowski's space-time did not make relativity less strange, but it made the strangeness more precise. Motion through space and motion through time became connected aspects of a single geometry. The speed of light became a defining feature of that geometry, marking the boundary between events that can influence each other and events that cannot. This is where light speed starts to look less like the speed of a thing and more like the structure of a rule. That is the deeper meaning of Einstein's change. Before special relativity, the speed of light seemed like a very large number attached to a very fast phenomenon. After special relativity, it became the invariant speed of space-time itself. It was the speed that all observers must agree on when measuring light in vacuum. It was the speed that forced time and distance to shift from one observer to another. It was the speed that began to define the possible paths of cause and effect. So the question is no longer only why light is so fast. The question is why the universe is built so that this speed remains fixed, while space and time bend their measurements around it. Einstein's answer was not a mechanical medium, not an ether wind, and not a hidden background through which light travels. The answer was a new structure of reality, one in which the speed of light is not just measured inside the universe, but helps define the universe's deepest order. Speed had once seemed like motion through space over time. Einstein showed that speed, at its deepest level, reveals what space and time are allowed to be. Time feels steady because in ordinary life it behaves so politely. A second on a kitchen clock seems like a second on a phone, a watch, a railway station display, and the slightly impatient microwave that appears to judge everyone equally. Time seems to flow in one shared direction at one shared rate, carrying everything along with it. People grow older together, days pass together. The world seems to agree on the pace of reality. Special relativity gently removes that agreement. One of its most surprising consequences is time dilation. Time dilation means that a moving clock ticks more slowly when measured by an observer who sees that clock moving. This does not mean the clock is damaged, confused, or suffering from a small mechanical, existential crisis. It means time itself is being measured differently, because motion through space and motion through time are connected. At very low speeds, the effect is tiny. At speeds close to the speed of light, it becomes dramatic. The simplest way to picture this is with a thought experiment called a light clock. Imagine 2 mirrors facing each other, one above the other, with a pulse of light bouncing between them. Each bounce from the lower mirror to the upper mirror and back again marks a tick of the clock. If the clock is sitting still beside you, the light simply travels straight up and down. The path is short and direct. Light moves from one mirror to the other, returns, and the clock ticks. Now imagine that same clock moving sideways at high speed. From the point of view of someone travelling along with the clock, nothing strange happens. The mirrors are still one above the other. The light still bounces straight up and down. The clock behaves normally in its own frame of reference. Locally, everything is calm, ordinary, and possibly in need of a cup of tea. But from the point of view of an outside observer watching the clock rush past, the light follows a different path. While the beam travels upward, the clock is also moving sideways, so the light does not appear to go straight up. It appears to trace a diagonal path. Then, as it travels downward, it traces another diagonal path. To the outside observer, the light has travelled a longer distance between ticks. Here is the crucial part. The speed of light in vacuum must remain the same for both observers. The moving clock cannot make light travel faster just because the path appears longer. So if the light travels a longer path while still moving at the same speed, the tick must take more time. The moving clock runs slow. That is the basic logic of time dilation. It is not caused by poor clock design. It is not a trick of perspective, like a distant object looking smaller. It is not simply that the clock appears slow because light takes time to reach the observer. After all those ordinary effects are accounted for, the result remains. A moving clock genuinely measures less elapsed time between the same two events when compared with a clock at rest, relative to the observer. This is strange because human beings are not built to notice relativistic effects. Walking, driving, flying, and even orbiting Earth involve speeds far below the speed of light. The difference in time is usually so small that ordinary senses never catch it. The body is excellent at detecting burnt toast, awkward silence, and someone opening a packet of crisps 3 rooms away, but it is not naturally equipped to detect tiny relativistic timing shifts. Physics, however, can. One of the most elegant natural examples comes from muons. Muons are unstable subatomic particles, similar in some ways to electrons but more massive. Many muons are created high in Earth's atmosphere when cosmic rays from space strike atoms in the air. These muons do not last long before decaying. In their own rest frame, their average lifetime is only a tiny fraction of a second, far too brief at ordinary expectations for many of them to reach the ground after being created high above. Yet many muons do reach Earth's surface. The explanation comes from special relativity. These muons travel at speeds close to the speed of light. From the perspective of observers on Earth, the muons' internal clocks run slowly. Their decay process is delayed relative to Earth's frame of reference, allowing more of them to survive the journey through the atmosphere. From the muon's own perspective, another relativistic effect can also be described. The atmosphere is length contracted, making the distance to the ground shorter. Both descriptions are consistent and both reflect the same underlying space-time geometry. The muons are not cheating death. They're simply moving through reality under rules that everyday intuition does not usually encounter. Time dilation has also been confirmed with human-made clocks. In 1971, Joseph Hafele and Richard Keating carried extremely precise atomic clocks on commercial aircraft flying around the world, both eastward and westward. When the travelling clocks were compared with atomic clocks left on the ground, tiny differences were found. The clocks had not all aged by exactly the same amount. The differences matched the predictions of relativity, once both special relativity and general relativity were included. Special relativity matters because the aircraft clocks were moving relative to the clocks on the ground. General relativity matters because clocks also tick differently, depending on gravitational conditions, including altitude. The full result was a blend of motion and gravity. It was a beautiful demonstration that time is not an invisible, universal drumbeat. It is something measured along paths through space-time. This is not just a laboratory curiosity. Modern satellite navigation depends on it. The Global Positioning System uses satellites carrying atomic clocks. These satellites orbit high above Earth, moving quickly relative to people on the ground. Their clocks are affected by special relativity because of their motion, and by general relativity because they are higher in Earth's gravitational field, where gravity is slightly weaker than at the surface. If these relativistic effects were ignored, satellite navigation would rapidly become inaccurate. The errors would build up until positions on Earth drifted by many kilometers. So when a phone uses satellite navigation to guide someone through an unfamiliar city, relativity is quietly working behind the scenes. The same theory that reshaped space and time is also helping people find the correct turning near a roundabout. This is perhaps not the most glamorous use of space-time, but it is extremely practical. Time dilation shows how reality protects its speed limit. If light speed must remain the same for all observers in uniform motion, then time cannot be absolute. It must adjust. Moving clocks must tick differently relative to other observers. The universe does not need a physical barrier at light speed, like a wall at the end of a racetrack. Instead, the structure of time itself changes the rules of motion. As an object moves faster, closer, and closer to the speed of light, the relationship between its motion through space and its passage through time becomes increasingly different from the ordinary view. For anything with mass, reaching light speed is not just hard, it is forbidden by the deeper structure of space-time. Time dilation is one of the signs of that structure revealing itself. The speed limit of reality is not defended by a cosmic police officer with a radar gun. It is defended by time. And time, as it turns out, is far less rigid than it first appears. Space feels solid because it behaves so reliably at human speeds. A room remains the same size whether someone is standing still or walking across it. A table does not appear to become shorter because it has been nudged slightly to the left. A car does not noticeably squash in the direction it's travelling, even when it's moving quickly down a motorway. Planes do not arrive looking thinner from nose to tail. Shopping trolleys, even the mildly ambitious ones with one wheel making independent life choices, do not become visibly compressed as they roll across a supermarket floor. And yet, special relativity says that space, like time, is not as rigid as it appears. The effect is called length contraction. It means that an object moving at very high speed is measured as shorter along the direction of its motion by an observer who sees it moving. The key phrase is along the direction of motion. A fast-moving spaceship would be measured as shorter from front to back, not equally squeezed in every direction like a cosmic accordion. Its height and width, measured perpendicular to its motion, are not contracted in the same way. This does not matter noticeably at everyday speeds. A car on a motorway is moving quickly by human standards, but it is still moving incredibly slowly compared with the speed of a light. A passenger jet feels impressive, and it certainly becomes more impressive when the snack trolley blocks the aisle for half the flight. But even a jet is nowhere near relativistic speed. The amount of length contraction is so tiny that no ordinary ruler, camera, or mildly suspicious passenger could notice it. Near light speed, however, the effect becomes significant. If a spacecraft could move at a large fraction of the speed of light relative to Earth, observers on Earth would measure it as shortened along its direction of travel. The faster it moved, the stronger the contraction would be. This is not because the spacecraft is physically crushed in its own frame of reference. Nothing inside the spacecraft would feel squeezed. The walls would not close in. The crew would not suddenly become thinner in one direction, which would be alarming, inconvenient, and very difficult to explain in a mission report. From the point of view of the people travelling with the spacecraft, everything inside remains normal. Their rulers measure normal lengths, their clocks tick normally, their seats, instruments, mugs, and knees remain as expected. In their own frame of reference, they are at rest. It is the distant universe outside that appears to behave differently. Distances in the direction of travel can appear contracted. This is one of the great lessons of relativity. Different observers can disagree about measured lengths and times without either observer being wrong. That sounds strange because everyday thinking treats length as absolute. A stick is assumed to have one true length. A road is assumed to have one true distance between its ends. A spacecraft is assumed to have one correct front-to-back measurement, and everyone else should simply accept it without making a fuss. But relativity shows that measured length depends on the observer's motion. The proper length of an object is the length measured in the frame where the object is at rest. Observers who see the object moving relative to them measure a contracted length along the motion. This is not a trick of eyesight. It is not the same as a moving object looking distorted because of camera exposure, viewing angle, or the time light takes to reach the eye. Relativistic visual appearances can be complicated, but length contraction is a deeper statement about measurement. It concerns how space and time coordinates differ between observers in relative motion, once the constant speed of light is built into the rules. The connection with time dilation is direct. Time dilation showed that moving clocks are measured to tick more slowly. Length contraction shows that moving distances are measured differently as well. They are not separate oddities sprinkled into physics for decoration. They're two faces of the same underlying space-time geometry. If the speed of light is to remain the same for all observers in uniform motion, then both time and space must adjust together. The mathematical relationship that describes this adjustment is called the Lorentz transformation. Hendrik Lorentz developed this transformation, while physicists were still trying to understand why the motion of Earth through the supposed luminiferous ether could not be detected. Later, in Einstein's special theory of relativity, the Lorentz transformation became part of a deeper interpretation. It no longer had to be seen as an object physically changing because it moved through an invisible ether. Instead, it described how measurements of space and time differ between observers moving relative to one another. In simple terms, the Lorentz transformation replaces the older Newtonian assumption that time is the same for everyone and space is measured the same way by everyone. Newtonian physics works beautifully when speeds are small compared with light speed. But near light speed, the Lorentz transformation shows that time intervals and distances must mix in a more subtle way. What one observer calls mostly distance, another observer may describe through a different combination of distance and time. This is where space begins to feel less like a fixed container and more like part of a flexible structure. The universe is not simply allowing objects to move through a rigid background, while time ticks universally above it all. Space and time are woven together into space-time. Motion changes how that fabric is divided into measurements of distance and measurements of duration. Length contraction also helps explain how the universe preserves the constant speed of light. In ordinary Newtonian thinking, speeds add simply. If a person walks forward inside a moving train, their speed relative to the ground is the train's speed plus their walking speed. This works wonderfully at low speeds. But if simple speed addition worked all the way up to light speed, then one might expect observers to measure light differently, depending on their own motion. A beam emitted from a moving source should seem faster or slower. Maxwell's electromagnetism and Einstein's relativity say otherwise. Light in vacuum is measured at the same speed by every observer in uniform motion. To make that possible, the universe cannot keep everyone's measurements of space and time identical. Distances and durations must shift together. Time dilation changes measured time. Length contraction changes measured distance. Combined through the Lorentz transformation, these effects prevent simple Newtonian velocity addition from pushing anything past light speed. This does not mean reality becomes chaotic or subjective in the casual sense. Relativity is not saying that everyone gets their own private universe where measurements can be whatever they like. It is the opposite. It gives exact rules for translating one observer's measurements into another's. The disagreement is structured, predictable, and experimentally confirmed. Observers may measure different lengths and times, but they agree on the underlying laws of physics. Length contraction is also useful for understanding high-speed particles. Muons created in Earth's atmosphere provide one example. From Earth's frame of reference, their lifetimes are extended by time dilation, allowing many to reach the ground. From the muon's own frame of reference, the distance through the atmosphere is contracted, so the journey is shorter. These are not competing explanations. They are two equally valid descriptions of the same physical reality from different frames of reference. That is the quiet brilliance of relativity. It allows nature to preserve one deep rule by changing things that once seemed unchangeable. Time can slow, space can shrink, simultaneity can depend on motion. But the speed of light in vacuum remains fixed. The speed limit of reality is not guarded by a barrier at the edge of motion. It is protected by the structure of space-time itself. As objects move faster and faster, the measurements of time and distance reshape around them. Space does not sit passively in the background. It participates. At ordinary speeds, space seems steady, generous, and uneventful. Near the speed of light, it reveals that even distance is part of the universe's deeper negotiation with motion. Adding speeds together feels so natural that it hardly seems like a rule at all. If you walk forward inside a moving train, your speed relative to the ground is your walking speed plus the train's speed. If you walk backward, your speed relative to the ground is the train's speed minus your walking speed. If someone throws a ball from a moving car, the ball carries the motion of the car and the extra motion of the throw. At ordinary speeds, this is exactly how the world appears to behave. Motion stacks neatly on motion, like adding one calm little number to another. This everyday rule is called Galilean velocity addition. It belongs to the older classical view of motion, where time is the same for everyone, distances are the same for everyone, and speeds combine in a straightforward way. It works extremely well in daily life because almost everything humans casually interact with moves very slowly compared with light. A running person, a racing car, a passenger jet, even a spacecraft in low Earth orbit, all move at tiny fractions of light speed. They may feel fast, especially if the seatbelt sign is on and the plane is making unpleasant little bumps in the clouds, but compared with light, they are barely stirring. This is why ordinary intuition survives so well. If a train moves at 100 kilometers per hour and someone walks forward inside it at 5 kilometers per hour, the person's speed relative to the ground is very close to 105 kilometers per hour. The classical answer works. The relativistic correction is so unbelievably tiny that it can be ignored. Newtonian mechanics and Galilean velocity addition are not bad tools. They are excellent tools within their proper range. The trouble begins near the speed of light. If ordinary addition worked perfectly at all speeds, then it would seem possible to overtake light simply by adding enough motion. Imagine a spacecraft already moving at nearly the speed of light. If it fired a smaller probe forward, classical intuition might suggest that the probe speed should be the spacecraft's speed plus the probe's launch speed. Keep doing that, and sooner or later, something should pass light. It sounds simple enough. Build a faster engine, add more speed, and eventually win the cosmic race. Special relativity says no. Near light speed, velocities do not add in the simple Newtonian way. Instead, they combine according to the relativistic velocity addition rule. The details can be written mathematically, but the meaning is more important here. When speeds are low, the relativistic rule gives almost the same answer as ordinary addition. That's why trains, cars, and thrown balls behave as expected. But when speeds become a significant fraction of light speed, the rule changes the outcome. No matter how speeds are combined, an object with mass cannot be pushed to light speed or beyond it. This is not because acceleration suddenly stops, as if the universe presses a large red emergency button. A rocket or particle can continue to accelerate, in the sense that energy continues to be added and momentum continues to increase. But as the object gets closer to light speed, added energy produces smaller and smaller increases in speed. The energy does not vanish. It changes the object's relativistic momentum and energy. The motion keeps changing, but not in the simple everyday way where each extra push gives a neat extra amount of speed. This is one of the places where common sense has to be handled gently, perhaps with a blanket and a warm drink. At low speeds, adding energy to an object mostly makes it move faster in an obvious way. Push a shopping trolley and it speeds up. Push it harder and it speeds up more, at least until one wheel swivels sideways and the trolley decides to become a philosophical problem. But near light speed, nature behaves differently. The closer something with mass gets to the speed of light, the harder it becomes to increase its speed by the same amount. The speed creeps closer and closer to the limit, but never reaches it. Particle accelerators show this beautifully. One of the most famous examples is the Large Hadron Collider at the European Organization for Nuclear Research, known as CERN. The Large Hadron Collider is a huge circular machine buried underground near Geneva, on the border between Switzerland and France. It accelerates protons to speeds extremely close to the speed of light before making them collide. These collisions allow physicists to study the fundamental particles and fields that make up matter, including the Higgs field and the particle associated with it, the Higgs boson. The protons in the Large Hadron Collider move so close to light speed that the difference is tiny compared with everyday experience. Yet even when enormous amounts of energy are added, the protons do not reach or exceed light speed. Instead, their energy rises dramatically. Their momentum increases. Their relativistic behavior becomes more extreme. But their speed approaches the speed of light only by smaller and smaller amounts. This is one of the clearest real-world demonstrations that the speed limit is not a matter of insufficient engineering. The issue is not that the machine is too weak, or that physicists have not found the correct cosmic accelerator pedal. The Large Hadron Collider is one of the most advanced scientific instruments ever built, and it can drive particles astonishingly close to light speed. But it cannot push protons all the way to the speed of light, because protons have rest mass. Anything with rest mass faces the same barrier. The deeper reason lies in the relationship between energy, momentum, space, and time. In Newtonian physics, momentum is simply mass multiplied by velocity. That works extremely well at low speeds. In relativity, momentum has a more subtle form because motion changes how energy and time behave. As an object approaches light speed, its energy and momentum increase without its speed increasing in the old linear way. The speed limit is not added on top of physics. It emerges from the structure of relativistic physics itself. This also explains why light is different. Photons, the particles of light, have no rest mass. They do not accelerate from rest up to light speed. In vacuum, they are always observed travelling at light speed. Massive particles, such as electrons, protons, atoms, spacecraft, planets, and sleepy humans wrapped in duvets, belong to a different category. They can move slowly, they can move quickly, they can approach light speed if enough energy is supplied, but they cannot become light-like. This is why velocity addition had to change. If the old rule were allowed to work everywhere, special relativity would collapse. Observers could measure different speeds for light depending on how they moved. Cause and effect could become unstable. Maxwell's electromagnetic theory would not fit the same way for different observers. The universe would lose the consistency that relativity preserves. Instead, nature uses a more careful rule. Low speeds combine almost exactly as expected, allowing daily life to remain pleasantly normal. High speeds combine in a way that protects the invariant speed of light. Space and time adjust through the Lorentz transformation. energy and momentum change according to relativistic laws. Acceleration remains possible, but light speed remains unreachable for matter. So the failure of ordinary speed addition is not a flaw in the universe. It is a sign of deeper order. Reality has a speed limit not because something blocks the path at the end, but because the ideas of distance, duration, energy and motion are linked more deeply than classical physics imagined. Near light speed, the universe stops behaving like a simple arithmetic problem and starts revealing the geometry underneath. At human speeds, motion can be added casually. Near light speed, motion becomes a negotiation with space-time itself. Mass is not just something matter has. It is also part of a deeper relationship with energy, motion, and the structure of space-time. This is one of the reasons the speed of light is not merely difficult to reach, like the top speed of a very stubborn machine. For anything with rest mass, light speed is physically unreachable. The universe does not simply make the journey hard. It changes the cost of the journey until the final step would require more energy than reality can provide. Albert Einstein's special theory of relativity revealed that mass and energy are not entirely separate things. The most famous expression of this idea is energy equals mass multiplied by the speed of light squared. It is probably the most recognizable equation in physics, partly because it is short, partly because it is profound, and partly because it has appeared on enough posters, mugs, and science classroom walls to qualify as a cultural landmark. But the idea behind it is not just decorative. It says that mass is a concentrated form of energy. Even an object sitting still, doing absolutely nothing dramatic, contains rest energy because it has mass. A stone resting on the ground, a cup sitting on a table, an atom inside a cell, and a proton inside an atomic nucleus all contain energy associated with their mass. Most of the time, that energy is not available in any obvious way. A mug of tea does not release nuclear scale energy just because someone looks at it thoughtfully, which is probably for the best. Mass energy equivalence becomes especially important in nuclear reactions. In the Sun, hydrogen nuclei fuse together through a chain of nuclear processes, eventually forming helium. The final helium nucleus has slightly less mass than the separate particles that went into making it. That missing mass has not vanished. It has been converted into energy, which eventually makes its way outward as sunlight. The light warming Earth began, in part, as a tiny difference in mass deep inside the Sun. This is why small amounts of mass can correspond to enormous amounts of energy. The speed of light is an enormous number, and multiplying by the speed of light squared makes the conversion factor vast. In nuclear power, particle physics, stellar fusion, and high-energy astrophysics, mass-energy equivalence is not an abstract idea. It is part of how stars shine, how unstable particles decay, and how matter and energy transform into one another under extreme conditions. But the same relativistic framework also explains why objects with mass cannot be accelerated to light speed. At low speeds, adding energy to an object usually makes it go faster in a familiar way. Push a ball and it speeds up. Fire a rocket engine and the rocket accelerates. Add more energy and its speed increases. This classical picture works well when speeds are small compared with the light speed, which is why everyday motion feels so intuitive. As an object moves closer to the speed of light, however, the relationship changes. Added energy still matters, but it no longer produces the same simple increase in speed. More and more of the added energy shows up as increased relativistic energy and momentum. The object continues to respond to force. It can keep gaining energy. It can keep gaining momentum. But its speed creeps closer to light speed by smaller and smaller amounts. This is sometimes explained by saying that the object becomes heavier as it moves faster. That phrase comes from an older way of describing relativity. using the idea of relativistic mass. It can be helpful as a rough image, but it can also be misleading. Modern physics usually avoids saying that the object's mass simply increases in the old-fashioned sense. Instead, physicists normally keep rest mass fixed and describe the change through relativistic energy and momentum. The distinction matters because a fast-moving proton has not turned into a different object with a new rest mass. A spacecraft moving quickly has not secretly gained extra matter inside its walls. What changes is the relationship between its motion, energy, and momentum as described by special relativity. The closer it gets to light speed, the more energy is required to produce any further increase in speed. Particle accelerators show this clearly. In machines such as the Large Hadron Collider at the European Organisation for Nuclear Research, known as CERN, protons are accelerated to speeds extremely close to light speed. The energy put into those protons becomes enormous compared with their rest energy. Their momentum increases dramatically. Their collisions can produce new particles, allowing physicists to study the deep structure of matter. But the protons do not reach light speed. They approach it extremely closely but never arrive. This is not a failure of the accelerator. It is not a matter of needing a slightly better power supply, a longer tunnel, or a physicist willing to press the go faster button with more confidence. The limit comes from the structure of relativity itself. For an object with rest mass, reaching light speed would require infinite energy. Since infinite energy is not available, the final step cannot be taken. That is the crucial point. The speed of light is not merely a difficult target. It is not like climbing a mountain, crossing an ocean, or building a faster spacecraft. Those are hard tasks, but they do not require infinity. Accelerating matter to light speed does. The closer an object with mass gets to that limit, the more severe the energy cost becomes, until the required energy grows without bound. Light itself is different because photons have no rest mass. They are not ordinary objects being accelerated up to light speed from rest. In vacuum, photons travel at the speed of light, because that is the only speed available to massless particles. Matter with rest, mass belongs to another category. It can move slowly, it can move quickly, it can move incredibly close to light speed under extreme conditions, but it cannot become light. This is how the universe enforces its speed limit through mass and energy. No wall appears in space. No warning sign flashes at the edge of motion. Instead, the rules of energy, momentum, and space-time gradually tighten. Every extra push has a smaller effect on speed. The object approaches the limit, but the limit retreats into an unreachable boundary. Reality has a speed limit because motion is not separate from energy, and energy is not separate from mass. To move faster is to enter a deeper relationship with space-time itself. For matter, the cost of chasing light rises without end, and so the universe allows massive objects to approach the fastest speed, but never to share it. Light is not the fastest thing in the universe because it tries harder. It is not pushing through space with an especially impressive engine, or sprinting across the cosmos with tiny glowing legs, which is probably for the best. Light travels at light speed because of what it is. More precisely, light travels at the speed of light in vacuum because its quantum particles, called photons, have no rest mass. That one detail changes everything. Objects made of ordinary matter have rest mass. A stone has rest mass. A planet has rest mass. A spacecraft has rest mass. A person sitting quietly under a blanket, making the wise decision not to accelerate toward light speed, also has rest mass. Rest mass means that an object can, at least in principle, be measured in a frame where it is not moving. It can be at rest. From there, it can be pushed, pulled, thrown, launched, or accelerated. But because it has rest mass, it can never be accelerated all the way to light speed. As it gets closer to that limit, The energy required grows without bound. Photons are different. A photon is a quantum particle of electromagnetic radiation. It is the particle associated with light, but also with every other form of electromagnetic radiation, including radio waves, microwaves, infrared radiation, ultraviolet radiation, X-rays, and gamma rays. These are not separate kinds of substance. They are all part of the electromagnetic field, differing in wavelength, frequency, and energy. The photon entered physics through the strange doorway of quantum theory. In 1905, the same remarkable year in which Albert Einstein published his work on special relativity, he also explained the photoelectric effect. The photoelectric effect is the emission of electrons from a material when light of a sufficiently high frequency shines on it. Classical wave ideas struggle to explain its details. Einstein proposed that light could behave as though its energy came in discrete packets, later called photons. This helped show that light was not only a wave in the classical electromagnetic sense, it also had particle-like quantum behavior. The later development of quantum mechanics turned that into a much richer picture, where light is described through the quantum behavior of the electromagnetic field. A photon is not a tiny glowing ball in the ordinary sense. It is a quantum excitation of that field. That phrase is a little technical, but the basic idea is gentle enough. A photon is one of the smallest possible packets of electromagnetic energy. Because photons have no rest mass, they do not behave like stones, spacecraft, or atoms. They cannot sit still in vacuum. There is no valid frame of reference in which a photon is at rest, waiting politely for someone to give it a push. A photon does not begin at rest and then accelerate up to light speed. In vacuum, photons are always observed travelling at light speed. This is a crucial difference. Matter with rest mass can move at many different speeds. It can be still relative to you. It can move slowly. It can move quickly. It can be pushed closer and closer to light speed if enough energy is supplied. But it cannot reach light speed. A photon, by contrast, does not have that range of possible resting and moving states. In vacuum, light speed is simply the speed at which it travels. That speed is about 300,000 kilometers per second. A beam of light could cross roughly 300,000 kilometers in 1 second, which is close to the average distance from Earth to the Moon, though the actual Moon is a little farther away. Light from the Moon takes a little over 1 second to reach Earth. Sunlight takes about 8 minutes to reach Earth. Light from the nearest stars takes years. Light from distant galaxies can travel for billions of years before entering a telescope. The universe is so large that even the fastest possible messenger spends most of its time simply being patient. There is one common point that can cause confusion. Light appears to slow down when it passes through materials such as glass, water, or air. This is why lenses bend light, why a straw can look kinked in a glass of water, and why prisms can spread white light into colours. But this slowing does not mean the fundamental speed limit has changed. Inside a material, light interacts with atoms and electrons. The electromagnetic wave is absorbed, re-emitted, delayed, and reshaped through its interaction with matter. The overall signal moves through the material more slowly than light travels through vacuum. This is described using the refractive index of the material. Glass has a higher refractive index than vacuum, so light takes longer to pass through it. Water does something similar. The photon story inside matter becomes more complicated because the light is no longer moving through empty space-time alone. It is moving through a crowded atomic landscape, and atoms are very good at making things slightly more awkward. In vacuum, however, the fundamental limit remains the same. The speed of light in vacuum is the speed that appears in special relativity, electromagnetism, and the structure of causality. It is the maximum speed at which information and influence can travel through space-time according to modern physics. Light is also not alone in revealing this limit. General relativity predicts that gravitational waves travel at light speed in vacuum. Gravitational waves are ripples in space-time produced by accelerating masses, especially extreme events such as merging black holes or neutron stars. Observations by the Laser Interferometer. Gravitational Wave Observatory and other detectors have strongly supported the idea that gravitational waves travel at essentially the same speed as light. This matters because it shows that the limit belongs not only to electromagnetic radiation, but to the causal structure of space-time itself. So light speed is not special because light is magical. Light is special because photons are massless, and massless phenomena reveal the universe's deepest speed limit directly. Light does not fight its way up to that speed. It does not overcome mass by being energetic enough. It travels that way because, without rest mass, it follows the light-like paths built into space-time. The name, speed of light, is therefore both accurate and slightly modest. It is the speed of light in vacuum, yes, but it is also the speed of causality. It is the speed of gravitational waves. It is the speed that separates what can influence what from what remains out of reach. It is the boundary that massive objects can approach but never share. Light can travel at light speed because light has no rest mass, and by doing so, it reveals that the fastest speed in the universe is not simply a property of brightness. It is a property of reality. Speed begins as a question of motion, but it does not stay there. At first, the speed of light seems to tell us how quickly something can move from one place to another. A beam leaves a star. A radio signal crosses space. A photon travels through vacuum at about 300,000 kilometers per second. This is already astonishing. But special relativity reveals a deeper meaning. The speed of light is not only the fastest speed at which light can travel, it is the fastest speed at which cause and effect can be connected. This is where the idea becomes quieter, stranger, and more important. Causality is the ordering of cause and effect. One event happens, and another event can respond to it only if some physical influence can pass between them. A hand pushes a cup, and the cup moves. A lamp switches on, and light travels across a room. A radio antenna sends a signal, and another antenna receives it. In each case, something carries influence from one event to another. The cause is not magically known everywhere at once. It must travel. In everyday life, this delay is usually too small to notice. Light crosses a room in a tiny fraction of a second, so the world feels immediate. Flick a switch, and the room appears bright. Speak to someone nearby, and the sound arrives so quickly that conversation feels naturally shared. But across larger distances, the delay becomes impossible to ignore. Light from the moon takes a little over 1 second to reach Earth. A signal from Mars can take several minutes, depending on where Mars and Earth are in their orbits. Light from the sun takes about 8 minutes to reach us. The universe is not instant. It is constantly waiting for influence to arrive. Special relativity gives this waiting a structure. Hermann Minkowski, who gave Einstein special relativity its space-time interpretation, showed that events can be thought of as points within a combined structure of space and time. An event might be something simple, a flash of light, a particle collision, a star exploding, a person sending a message, or a kettle clicking off with the quiet authority of a small household finale. Each event sits somewhere in space-time. The question is whether that event can influence another event. The answer is described using light cones. A light cone is a way of mapping the possible paths that light, information, or influence can take from a single event. Imagine a flash occurring at one point. Light spreads outward in all directions. As time passes, the sphere of light grows larger. If this spreading is drawn in a spacetime diagram, with time upward and space outward, the expanding sphere becomes a cone shape. This is the future light cone of the event. Anything inside the cone could, in principle, be affected by the flash, because a signal travelling at or below light speed could reach it. There is also a past light cone. This includes all the events that could have influenced the original event. If a signal from some earlier place and time could have reached the flash before it happened, then that earlier event lies inside its past light cone. The past light cone contains possible causes. The future light cone contains possible effects. This is a beautifully simple idea with enormous consequences. Events inside one another's light cones can be causally connected. Events outside those light cones cannot. Not because the universe is being unhelpful, but because no physical signal travelling at or below light speed can cross the separation in time. The speed of light draws a boundary between what can affect what and what cannot. Physicists describe these relationships using the terms time-like, light-like, and space-like separation. Time-like separation means two events are close enough in space and separated enough in time that one could influence the other by travelling slower than light. A person could move from one event to the other. A spacecraft, a message, a particle, or some ordinary physical process could connect them. The cause and effect relationship is possible. Light-like separation means two events can be connected only by something travelling at exactly light speed, such as a photon in vacuum or a gravitational wave in vacuum. A beam of light leaving one event could arrive at the other, but anything slower would not make it in time. Space-like separation means the events are too far apart in space and too close together in time for any light speed or slower signal to connect them. They are outside each other's causal reach. One cannot be the cause of the other in the ordinary physical sense, because no influence could travel between them quickly enough. This is not just abstract geometry. It is the universe's way of keeping events organized. If faster than light signaling were possible, causality would become deeply unstable. A message could be sent from one place to another faster than light. That already sounds strange, but relativity makes it stranger still, because different observers moving relative to one another can disagree about the timing of distant events. Some observers could describe the message as arriving before it was sent. With the right arrangement, faster-than-light communication could open the door to causal loops, where an effect appears before its cause. That is not just a dramatic inconvenience. It would undermine the basic structure that allows physical events to be ordered. If a message can arrive before it is sent, then the difference between cause and effect becomes blurred. A person could, in principle, send information into their own past, and once that possibility appears, physics begins collecting paradoxes like someone with an over-enthusiastic stamp album. This is why the speed limit of reality matters so much. It does not merely stop rockets from reaching inconveniently high speeds. It protects the order of events. It preserves the difference between what has happened, what can happen, and what cannot be reached in time. It gives space-time a causal structure. Minkowski's space-time geometry makes this structure visual and precise. The speed of light is not simply one line among many. It forms the boundary of the light cone. Inside the cone, cause and effect can operate. Outside the cone, events remain separated from one another in a way that no ordinary signal can overcome. The speed of light is therefore not just a speed. It is the slope of possibility in space-time. This is why distant astronomy is also a study of causal delay. When telescopes observe a galaxy millions or billions of light-years away, they are not seeing that galaxy as it is right now in some universal present. They are seeing light that has only just arrived after travelling for immense stretches of time. The galaxy may have changed, stars may have died, new stars may have formed. but none of that later information has reached us yet. The universe does not reveal itself all at once. It releases its history at light speed. Even nearby space obeys the same rule. If the sun somehow changed suddenly, Earth would not know immediately. The information carried by light and gravity would take about 8 minutes to reach us. This does not mean the sun is likely to perform such a rude trick. It simply shows that influence is not instantaneous, even for the star that dominates our sky. Reality's speed limit is therefore a rule about communication in the deepest sense. Not conversation, not language, but physical communication. The passing of influence from one event to another. Light, gravity, particles, fields, and information all obey the causal structure of space-time. The limit tells the universe where cause and effect can go. So the speed of a light is not only the answer to how fast light moves, it is the answer to a deeper question. How quickly can reality update itself from one place to another? And the answer is finite. The universe does not permit every event to touch every other event instantly. It allows influence to travel, but only along paths that space-time permits. Cause and effect are not free to leap anywhere they like. They move inside the boundaries drawn by light. That boundary is not a prison. It is the reason the story of the universe can be told in order. It is tempting to imagine that faster-than-light travel would simply make the universe more convenient. Stars would no longer feel impossibly distant. Messages could cross interstellar space without waiting years, centuries, or millennia. A spacecraft could leave Earth and reach another star within a human lifetime, perhaps even within a long weekend, depending on how ambitious the itinerary became. The galaxy would shrink from an ocean of unreachable distances into something more like a very large neighbourhood, although admittedly one with poor parking and an alarming amount of radiation. But in physics, faster-than-light motion is not just a question of going very quickly. It is not merely a better engine, a stronger rocket, or a clever shortcut around cosmic impatience. According to special relativity, faster-than-light signalling would disturb something far more basic than travel time. It would threaten the order of cause and effect. This is why faster-than-light travel has to be handled carefully. It is useful as a thought experiment, because it reveals why the speed limit matters. But it is not an accepted physical possibility for ordinary objects or signals moving through ordinary space-time. No experiment has shown that matter, information, or usable signals can travel faster than light in vacuum. The speed limit remains one of the most deeply tested principles in modern physics. The problem begins with causality. Causality means that causes come before their effects. A message is sent before it is received. A glass is pushed before it falls. A star explodes before the light from that explosion reaches a telescope. In everyday life, this order feels obvious, but relativity shows that the timing of distant events depends on the motion of the observer. Observers moving relative to one another can disagree about whether two far apart events happened at the same time. That is already strange, but it remains safe as long as no influence travels faster than light. The speed of light protects the structure. Events outside one another's light cones cannot communicate. They may be arranged differently in time by different observers, but because no signal can pass between them, no contradiction is created. The universe can tolerate disagreement about the order of events that cannot affect one another. It is rather like two people disagreeing about which distant cloud looked slightly more like a potato. The disagreement may be spirited, but nothing important collapses. Faster-than-light signalling would change that. If a signal could travel faster than light from one event to another, then there could be observers who see that signal as arriving before it was sent. This is not just a visual illusion. It follows from the geometry of space-time in special relativity. Because time and space mix differently for observers in relative motion, a faster-than-light path can tilt outside the light cone in a way that reverses the time order for some observers. With the right arrangement, messages could be sent into the sender's own past. That creates causal paradoxes. A person might receive a warning before deciding whether to send it. A message could prevent the event that caused the message to be sent. Signal could become part of a loop with no clear beginning. Physics does not enjoy this sort of thing. It prefers cause and effect to form something tidier than a snake trying to swallow its own calendar. This is one reason hypothetical faster-than-light particles called tachyons are treated with caution. Tachyons appear in some speculative theoretical discussions as particles that would always move faster than light. The word comes from a Greek root meaning swift, which is certainly fair branding. But tachyons have never been observed. They are not part of established particle physics as real detected objects. In modern theory, tachyon-like features often signal an instability in a model, rather than a usable, faster-than-light particle waiting to be caught. The important distinction is between mathematics and reality. A mathematical idea can be explored without being physically realized in nature. Physicists often investigate strange possibilities because they help reveal what a theory allows, what it forbids, and where it might break. Tachyons are useful in that sense. They help sharpen the question of what faster-than-light motion would mean. But there is no experimental evidence that tachyons exist as particles carrying usable information through the universe. Science fiction has spent a long time trying to imagine ways around the problem, and understandably so. Faster-than-light travel is almost necessary if stories want people to cross the galaxy, without spending most of the plot waiting quietly in a metal tube. Warp drives, hyperspace, jump gates, wormholes, and other shortcuts are imaginative responses to a real barrier. They are storytelling tools built around a genuine physical difficulty. Ordinary motion through space cannot carry matter faster than light. Some of these ideas have loose connections to real physics. General relativity describes gravity as the curvature of space-time, and space-time itself can have surprising geometries. The expanding universe already shows that distant galaxies can recede faster than light, because space itself is stretching between them. That does not allow local faster-than-light travel, but it does show that space-time geometry is more flexible than old Newtonian intuition suggested. One of the most famous scientific warp concepts was proposed by Miguel Alcubierre in 1994. The Alcubierre warp drive is a solution within general relativity in which a region of space-time, often described as a warp bubble, moves in an unusual way. Space would contract in front of the bubble and expand behind it. The spaceship inside would not locally move faster than light through nearby space. Instead, the geometry of space-time would change around it, allowing the bubble to produce an effective faster-than-light journey as seen from far away. This is a clever idea because it tries to avoid breaking the local rule that nothing moves through its immediate surroundings faster than light. The ship inside the bubble could remain locally at rest, while the space-time bubble does the exotic work. It is less like driving a car faster than light and more like persuading the road to move, which sounds wonderfully convenient until the road asks for impossible physics in return. The problems are enormous. The Alcubierre warp drive appears to require exotic energy conditions, often associated with negative energy density. In ordinary terms, it seems to need forms of energy and matter arranged in ways not known to be physically achievable on the required scale. Some later work has explored whether the requirements could be reduced or modified, but the concept remains speculative. It is not an engineering design waiting for a large enough budget and a confident enough launch speech. There are also stability questions. Even if a warp bubble could exist mathematically, creating it, controlling it, entering it, leaving it, and preventing destructive effects are separate and unresolved issues. The bubble may involve horizons that make it difficult for the occupants to control the front of the warp region. There are questions about radiation, quantum effects, and whether the required space-time shape could be sustained at all. Causality remains a concern as well. Many faster-than-light concepts, even when framed through space-time geometry, risk allowing closed causal curves or time travel-like behavior under certain conditions. A closed causal curve is a path through space-time that returns to its own past. General relativity permits some mathematical solutions with this kind of structure, but that does not mean nature allows them physically. Stephen Hawking famously suggested the chronology protection conjecture, the idea that the laws of physics may prevent time machines from forming. It remains an open question rather than a proven principle, but it reflects the seriousness of the causality problem. Hyperspace is even more speculative. In fiction, hyperspace usually means leaving ordinary space, travelling through another dimension or shortcut region, and re-emerging somewhere distant. In real physics, there is no confirmed hyperspace travel mechanism. Some theories, such as certain versions of string theory, discuss extra dimensions mathematically, but those ideas do not provide a demonstrated route for spacecraft to bypass light speed. Extra dimensions, if they exist, are not known to function as a convenient cosmic side road. Wormholes are another famous possibility. General relativity allows mathematical solutions resembling tunnels through space-time, sometimes called Einstein-Rosen bridges. But traversable wormholes, if they are possible at all, appear to require exotic matter or negative energy to hold them open. They also raise serious stability and causality problems. Like warp drives, wormholes sit in the fascinating borderland between serious mathematics and unproven physical possibility, so faster-than-light ideas fall into different categories. There is confirmed physics, where no usable faster-than-light motion or communication has been observed. There are speculative particles like tachyons, which remain undetected and are not part of established reality. There are mathematical space-time models like the Alcubierre warp drive, which explore what the equations of general relativity might permit under extreme and possibly impossible conditions. And there is science fiction, which is allowed to be much more relaxed about fuel requirements, causality, and the unfortunate paperwork involved in arriving before departure. The central point is not that imagination is useless. Imagination is vital in science. Many real discoveries began as strange questions, but physics must separate what is mathematically interesting from what is experimentally supported. Faster-than-light travel has not been shown to be possible for objects or signals in ordinary space-time. The speed of light remains the boundary that confirmed physics respects, and that boundary is not merely about limiting motion. It protects causality. It keeps messages from arriving before they are sent. It keeps causes on one side and effects on the other. It allows the universe to have a coherent order even when observers disagree about time and distance. Faster-than-light travel sounds like freedom, but in relativity, it may be the kind of freedom that breaks the clock, muddles the message, and leaves cause and effect staring awkwardly at each other across space-time. The universe's speed limit is not just stopping rockets from going faster, it is keeping reality from tying itself in knots. Gravity once seemed as though it might be instantaneous. In Isaac Newton's picture of the universe, every object with mass attracted every other object with mass through the force of gravity. Earth pulled on the moon pulled on Earth, the sun pulled on the planets, and the planets pulled back on the sun. This was described with extraordinary mathematical success. Newton's law of universal gravitation explained planetary orbits, tides, falling bodies, and the elegant clockwork of the solar system with a precision that changed science forever. but there was a quiet unease hidden inside the picture. Newton's gravity seemed to act across empty space. The sun was far from Earth, yet Earth continually curved around it. The moon was far from the oceans, yet tides rose and fell under its influence. In Newtonian physics, gravity appeared to reach across distance immediately, as though every mass in the universe somehow knew where every other mass was at once. Newton himself was cautious about this idea. He could describe gravity's behaviour with stunning accuracy, but the mechanism behind action at a distance remained mysterious. If the sun could somehow vanish, in the old Newtonian picture, Earth might be expected to feel the gravitational change immediately. Of course, the sun is not planning this particular trick, which is considerate of it, but as a thought experiment, it reveals the problem. Instant gravity would mean that information about a change in mass could travel across space with no delay at all. That would clash with the deeper relativistic picture in which no signal, influence, or information can travel faster than light. Albert Einstein faced this problem after special relativity. His theory had changed the meaning of space, time, and motion, but it did not yet fully explain gravity. Special relativity dealt with observers moving uniformly, without acceleration or strong gravitational fields. Gravity needed something larger. In 1915, Einstein presented the general theory of relativity, one of the most profound shifts in the history of physics. General relativity describes gravity not as an invisible force pulling instantly across a fixed background, but as the curvature of space-time itself. Matter and energy shape space-time, and the shape of space-time guides the motion of matter and energy. A planet orbiting the sun is not being tugged by an instant signal through empty nothingness in the old sense. It is moving along a path shaped by the curved space-time around the sun. This is often pictured with a stretched rubber sheet, where a heavy ball creates a dip and smaller balls roll around it. That image is useful, but limited. Real space-time is not a two-dimensional sheet bending into a higher room. It is the four-dimensional structure of space and time, and gravity is its curvature. Still, the simple picture helps suggest the main idea. Gravity belongs to geometry. It is not simply something happening inside space-time. It is something space-time is doing. And if gravity is part of space-time, then changes in gravity cannot update the whole universe instantly. In general relativity, changes in the gravitational field propagate at the speed of light. If a massive object moves, collapses, or merges with another massive object, the change in space-time does not become known everywhere at once. It travels outward. Gravity obeys the same causal limit that light does. This was a crucial transformation. The speed limit was no longer just a rule for electromagnetic waves. It had become part of the behavior of gravity itself. One of the most beautiful predictions of general relativity is the existence of gravitational waves. Gravitational waves are ripples in space-time produced by accelerating massive objects. In everyday life, moving objects create gravitational waves so tiny that they are hopelessly undetectable. A person waving a hand technically disturbs space-time, but only in a way so absurdly small that the universe seems to politely ignore it. The most powerful gravitational waves come from extreme cosmic systems. Orbiting black holes, neutron stars, and other dense objects can stir space-time strongly enough to send ripples outward across the universe. As two massive objects spiral around each other, they lose energy through gravitational waves. Their orbit shrinks. They circle faster and faster. Finally, they merge, releasing an enormous burst of gravitational wave energy. For decades, gravitational waves were a prediction waiting for direct detection. Indirect evidence came earlier from the Hulse-Taylor binary pulsar, discovered by Russell Hulse and Joseph Taylor in the 1970s. This pair of neutron stars was observed gradually losing orbital energy in a way that matched the prediction of gravitational wave emission from general relativity. It was a remarkable confirmation, but the waves themselves had still not been directly measured on Earth. That changed with the Laser Interferometer Gravitational Wave Observatory, known as LIGO. LIGO is a pair of extremely sensitive detectors in the United States, designed to measure unimaginably tiny changes in distance caused by passing gravitational waves. Each detector uses long arms with laser beams traveling through them, allowing scientists to detect stretching and squeezing of space-time far smaller than the width of a proton. That may sound like measuring whether the Atlantic Ocean has changed by less than the width of a hair, except even that comparison is far too generous. In 2016, LIGO announced the first direct detection of gravitational waves. The signal had been observed in 2015 and came from the merger of two black holes more than 1 billion light-years away. For a brief moment, that collision released gravitational wave power on a scale almost impossible to imagine. By the time the waves reached Earth, they were incredibly faint, yet still measurable by LIGO's instruments. This detection was a triumph for general relativity. It showed that space-time really can ripple. It confirmed that black holes behave in ways predicted by Einstein's theory, and it supported the idea that gravitational influence travels at light speed, not instantly. An even more dramatic test came in 2017, when gravitational waves from a neutron-star merger were detected. This event was especially important because it was also seen in light. Telescopes around the world observed electromagnetic radiation from the same cosmic collision, including gamma rays and visible light. The gravitational waves and light had travelled across space for an immense time and arrived at Earth very close together. That near-simultaneous arrival placed extremely strong limits on any possible difference between the speed of gravitational waves and the speed of light. If gravity travelled at a very different speed from light, the delay after such a long journey would have been much larger. Instead, the observation showed that gravitational waves and light move at essentially the same speed through vacuum within very tight measurement limits. This matters deeply for the idea of a universal speed limit. Light speed is not only about light. It is not merely a property of lamps, lasers, stars, or photons. General relativity shows that the same limit applies to gravitational changes in space-time. When black holes merge, the gravitational news does not arrive instantly. When neutron stars collide, the ripples in space-time do not outrun causality. They travel at the speed permitted by the structure of reality. This brings gravity into the same story as electromagnetism, special relativity, and causality. The universe does not have one rule for light and a separate instant rule for gravity. The causal structure is shared. Light waves, gravitational waves, and information about physical changes all respect the same boundary. That is why the speed limit belongs to space-time itself. It is not a practical inconvenience imposed on rockets. It is not just the speed of bright things. It is the rate at which reality allows influence to move outward through the cosmic fabric. Gravity, the force that shapes planets, stars, galaxies, black holes, and the expansion history of the universe, also obeys that limit. Newton gave gravity its first great mathematical voice. Einstein taught gravity to speak the language of space-time, and when space-time ripples, even gravity travels no faster than light. A black hole is what happens when gravity becomes so extreme that the idea of escape changes completely. In ordinary life, escape is mostly a question of speed and direction. Throw a ball upward gently, and it falls back down. Throw it faster, and it climbs higher before returning. Fire a rocket with enough speed, and it can escape Earth's gravity entirely, leaving the planet behind and entering space. This idea leads naturally to escape velocity, the speed an object needs to break free from a gravitational body without further propulsion. For Earth, escape velocity is high, but achievable by rockets. For the Sun, it is much higher. For a very dense object, where a lot of mass is packed into a small region, escape velocity can become enormous. In a simple Newtonian picture, one might imagine an object so compact that its escape velocity exceeds the speed of light. Since nothing can move faster than light, even light would be unable to escape. This is a useful first step toward imagining a black hole, but it is only a first step. A real black hole is not best understood as a place where light tries to escape and gets tired, like a weary traveller deciding the hill is too steep and returning home for a biscuit. Light does not slow down because it lacks determination. In vacuum, light always moves at light speed. The reason light cannot escape from inside a black hole is deeper. The geometry of space-time has changed so severely that all future paths inside the boundary lead inward. That boundary is called the event horizon. The event horizon is not a solid surface. It is not a shell, a wall, or a glowing membrane that a falling object would necessarily bump into. For a large black hole, crossing the event horizon might be locally uneventful at first, which is a deeply unsettling sentence when said calmly enough. The event horizon is a causal boundary. It marks the point beyond which no signal moving at or below light speed can ever reach the outside universe. This is where black holes connect directly to the speed limit of reality. If signals could travel faster than light, the event horizon would not have the same meaning. But because light speed is the maximum speed of causality, the event horizon becomes a one-way boundary in space-time. Once inside, every future directed path that matter or light can take leads deeper inward. Escaping is not merely difficult. It is not one extra burst of engine power away. It is no longer part of the available future. The first exact black hole solution to Einstein's field equations was found by Carl Schwarzschild in 1916, only shortly after Einstein presented the general theory of relativity in 1915. Schwarzschild was serving during the First World War when he developed this solution, which described the space-time outside a perfectly spherical, non-rotating mass. The Schwarzschild solution revealed something remarkable. If enough mass were compressed inside a certain radius, the mathematics produced an event horizon. This radius is now called the Schwarzschild radius. For any given mass, it describes how small that mass would need to be compressed for an event horizon to form. Earth would have to be squeezed down to a size smaller than a marble to become a black hole. The Sun would need to be compressed to a radius of only a few kilometers. These comparisons are rough, but they show the central point. Black holes are not formed merely by having mass. They are formed when mass is concentrated so tightly that space-time closes causal escape routes. The Newtonian idea of escape velocity remains helpful, but it can mislead if taken too literally. In Newton's physics, gravity is a force pulling objects across space. In general relativity, gravity is the curvature of space-time. A black hole is not simply a stronger version of a planet, pulling harder and harder until even light is dragged back. It is a region where space-time itself is shaped in such a way that outward escape paths disappear. Outside the event horizon, escape is still possible. A spacecraft with enough thrust, or a photon travelling in the right direction from outside the boundary can move away. But at the event horizon, the outward path for light becomes balanced on the edge of impossibility. Inside it, even light directed outward cannot increase its distance from the black hole in the way it would outside. The future direction points inward, toward the central region where classical general relativity predicts a singularity. The singularity is another sign that the current theory is incomplete at the deepest level. General relativity predicts that density and space-time curvature become infinite at the center of an idealized black hole, but most physicists expect that a full theory of quantum gravity would be needed to understand what truly happens there. The event horizon, however, is not merely a mathematical curiosity. It has real astrophysical consequences, and black holes are now strongly supported by observation. One of the most famous modern examples comes from the Event Horizon Telescope. This global network of radio observatories uses a technique called very long baseline interferometry, combining telescopes across Earth to create an effective planet-sized instrument. In 2019, the Event Horizon Telescope collaboration released the first image of the shadow of a supermassive black hole in the galaxy Messier 87. The image showed a bright ring of emission around a dark central region, produced by hot material near the black hole and the bending of light by extreme gravity. In 2022, the Event Horizon Telescope collaboration released an image of Sagittarius A star, the supermassive black hole at the centre of the Milky Way. Sagittarius A star is far less massive than the black hole in Messier 87, but it sits in our own galaxy, about 27,000 light-years away. These images are not photographs of the event horizon as a surface. Rather, they show the glowing material and distorted light around regions where space-time is so curved that a central shadow appears. Black holes therefore make the speed limit of reality feel almost tangible. They are places where the fastest possible signals still cannot cross a certain boundary outward. A radio message from inside the event horizon cannot reach a receiver outside. A flash of light cannot escape. A gravitational signal produced inside cannot carry information back into the wider universe. The causal structure has been sealed. This does not happen because black holes are magical vacuum cleaners. They do not suck in the universe indiscriminately. Far from a black hole, gravity behaves like the gravity of any other object with the same mass. If the Sun could somehow be replaced by a black hole of equal mass, Earth would not be immediately swallowed. It would continue orbiting in much the same way, although the lack of sunlight would make the situation biologically unpopular. The true strangeness of a black hole lies not in suction, but in causality. It is a region where space-time has been curved so profoundly that the future becomes one way. The speed of light still rules. Light still travels at light speed, but the paths available to light have changed. Reality has a speed limit, and black holes reveal what happens when space-time itself turns that limit into an edge of escape. Even the fastest thing cannot outrun a future that points inward. At first glance, the expanding universe seems to break the very rule that has been carefully protected all along. If nothing can travel faster than light, how can distant galaxies be receding from us faster than light? It sounds like a contradiction, the sort of thing that makes the universe seem as though it has hidden a small loophole in the terms and conditions. But the key is that cosmic expansion is not quite the same as ordinary motion through space. Special relativity limits how fast objects, signals, and information can move through local space. A spacecraft cannot fly past you faster than light. A radio message cannot outrun light through its immediate surroundings. A particle with rest mass cannot be accelerated up to light speed. These limits apply locally, in the nearby region of space-time where motion can be measured in the usual relativistic way. The expansion of the universe is different. It is not best understood as galaxies flying away through space from a central explosion point. Instead, space itself is stretching between galaxies. On very large scales, the distance between far apart galaxies increases because the fabric of the universe is expanding. The galaxies are not necessarily speeding through their local neighborhoods faster than light. Rather, the amount of space between them and us is growing. This is one of the strange gifts of general relativity. Space is not a fixed container. It can curve, it can stretch, it can evolve. In the large-scale universe, the geometry of space-time changes over cosmic time, and that changing geometry allows distant regions to recede from one another in a way that does not behave like an ordinary rocket race. The expanding universe picture began to take shape in the early 20th century. Georges Lemaitre, a Belgian physicist and priest, used general relativity to propose that the universe was expanding. He connected theory with observations of distant galaxies and suggested that the cosmos had evolved from a hotter, denser earlier state. Edwin Hubble, working with observations from Mount Wilson Observatory, found a relationship between the distances of galaxies and the redshifts in their light. The farther away a galaxy was, the more strongly its light tended to be shifted toward longer, redder wavelengths. This became known as Hubble's law, though the history also properly includes Lemaitr's important theoretical and observational role. In words, Hubble's law says that more distant galaxies generally recede faster from us, not because Earth sits at the centre of the universe, but because every distant observer in a broadly uniform expanding universe would see a similar pattern. More space between two galaxies means more expanding space, so the total separation grows faster. A useful comparison is a loaf of raisin bread rising in an oven. As the dough expands, every raisin sees the other raisins moving away. The farther away a raisin is, the more dough there is between them, and the faster the separation grows. The raisins are not crawling through the bread. The bread itself is expanding. This comparison is imperfect, as all kitchen-based cosmology eventually becomes, but it captures the main idea gently enough. Over small distances, cosmic expansion is tiny. Gravity holds galaxies, star systems, planets, and people together. The Milky Way is not expanding in any meaningful everyday sense. Earth is not slowly inflating like a troubled balloon. The space inside a cup of tea is not participating in cosmic expansion in a way anyone needs to worry about. Bound systems resist the expansion because local forces dominate. Across enormous distances, however, expansion adds up. A galaxy far enough away can have a recession speed greater than the speed of light, not because it is locally moving through space faster than light, but because the space between here and there is stretching rapidly enough that the total distance increases faster than light could cross it. This does not allow faster-than-light messaging. A civilization in such a distant galaxy could not simply send a signal through local space faster than light. Their light still travels locally at light speed. Their radio waves still obey the causal structure of space-time. The faster-than-light recession comes from the large-scale expansion of space, not from any object breaking the local speed limit. This distinction matters because relativity is local at its core. In a small enough region of space-time, the speed of light remains the maximum speed of causal influence. But across the enormous, curved, evolving universe, distances can change because space-time itself is dynamic. The rules are not being ignored. They are being applied in a larger and subtler setting. Light speed still shapes what can be seen. The observable universe is the region from which light has had time to reach us since the hot early stages of the cosmos. It is not the whole universe, as far as modern cosmology can tell. It is the part of the universe that is visible to us because signals have had enough cosmic time to arrive. Beyond that lies more universe that may exist but has not had time to send light here. The particle horizon marks the boundary of how far we can see in principle, based on the age of the universe and the history of cosmic expansion. Because the universe has expanded while light has travelled, the most distant regions we can observe are now much farther away than 13.8 billion light-years. Their light has been travelling for most of cosmic history, while space has stretched during the journey. There is also a cosmic event horizon in our accelerating universe. Because the expansion of the universe is speeding up, driven by what cosmologists call dark energy, some distant regions are moving away in such a way that light emitted from them now may never reach us. Likewise, light sent from us today may never reach certain faraway galaxies. This is not because the light gives up. It is because the space between grows too quickly for the signal ever to close the distance. That is a quiet and enormous idea. The speed of light does not merely affect rockets, lasers and particles. It shapes the limits of cosmic knowledge. It determines what parts of the universe can be observed, what parts can be contacted, and what parts are already slipping beyond any possible future exchange of information. So the universe can expand in a way that makes very distant galaxies recede faster than light, sort of. But that phrase hides the crucial difference. Nothing locally outruns a beam of light through nearby space. No message cheats causality. No spacecraft escapes relativity by simply moving fast enough. Instead, the large-scale geometry of the universe changes the meaning of distance across cosmic time. Reality still has a speed limit, but space-time is not merely the road on which everything moves. On the larger scale, space-time is also changing the length of the road itself. Quantum entanglement has a habit of sounding as though the universe has found a way to whisper instantly across space. Two particles can be created or prepared so that their properties are not fully independent, even when they are separated by a great distance. Measure one, and the result is correlated with the result found for the other. The connection can be stronger than anything allowed by ordinary classical physics. It is real, experimentally supported, and genuinely strange. It is also one of the easiest places to accidentally imagine that the speed limit of reality has been broken. But entanglement is more subtle than instant messaging. In quantum physics, particles are described by quantum states. These states do not always assign simple pre-existing values to every property before measurement. In some cases, two or more systems must be described together as one shared quantum state, even if the individual parts later move far apart. When that happens, the systems are entangled. Their measurement results are linked in a way that cannot be fully explained by saying each particle simply carried a hidden instruction card from the beginning. This troubled Albert Einstein deeply. Einstein helped create quantum theory, especially through his work on photons and the photoelectric effect. But he was never comfortable with the idea that quantum mechanics might be complete in its standard form. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published an argument now known as the Einstein-Podolsky-Rosen argument. They suggested that quantum mechanics might be incomplete because it seemed to allow distant particles to be connected in a way that challenged locality. Locality is the principle that objects are directly influenced only by their immediate surroundings, and that any influence between distant objects must travel through space at no faster than light speed. Einstein worried that quantum mechanics seemed to involve what he famously criticized as spooky action at a distance. The phrase is memorable, partly because it sounds like the universe has been caught wearing a bedsheet in a dark hallway. But the concern behind it was serious. If measuring one particle appeared to affect another distant particle instantly, what did that mean for relativity? One possible answer was hidden variables. Perhaps quantum particles really did carry definite properties all along, but quantum mechanics simply did not describe those deeper details. If that were true, then entanglement might be less mysterious. The particles would not be influencing one another instantly. They would merely be revealing prearranged information when measured, like two envelopes opened in different rooms. For a while, this sounded like a philosophical debate that experiments might never settle. Then came John Bell. In the 1960s, John Bell developed Bell's theorem, one of the most important results in the foundations of quantum physics. Bell showed that if local hidden variables explained quantum correlations, then certain measurable limits would have to be obeyed. These limits became known as Bell inequalities. Quantum mechanics predicted that entangled particles could violate those inequalities. In other words, the debate could be tested. Experiments later showed that nature violates Bell inequalities in the way quantum mechanics predicts. Alain Aspect and his colleagues carried out influential experiments in the early 1980s, providing strong evidence against simple local hidden variable explanations. Later experiments reduced major loopholes, making the case even stronger. These loophole-reduced Bell test experiments have supported the conclusion that the quantum world does not behave like a classical world with merely hidden pre-written instructions. This is extraordinary. Entangled systems really do share correlations that go beyond classical expectations. Nature appears to be non-classical in a deep way. But this still does not mean faster than light communication is possible. The reason is that entanglement produces correlations, not controllable messages. When one person measures one particle from an entangled pair, the result they get is not something they can choose freely in order to send a signal. The outcome appears random. When another person later measures the distant partner particle, their outcome is also locally random. Only when the two observers compare their results through ordinary communication do the correlations become clear, and that comparison requires a normal signal, which cannot travel faster than light. This point is captured by the no communication theorem. In clear terms, the theorem says that entanglement cannot be used to transmit usable information faster than light. Measurements on one part of an entangled system cannot be controlled in a way that sends a readable message to the other part instantly. The distant observer cannot look at their particle alone and tell whether, when, or how the first particle was measured. Their local results look random until classical communication brings both sets of data together. So entanglement does not overthrow relativity. It unsettles classical intuition, but it does not allow causal signaling faster than light. The universe permits quantum correlations that are stronger than expected, yet still prevents those correlations from becoming instant communication. This is one of the most fascinating balances in modern physics. Quantum mechanics seems to tell us that reality is less separable than it appears. Relativity tells us that information and influence cannot outrun light. At first, these ideas seem to pull against each other, but the confirmed physics respects both. Entanglement is real. Bell's theorem is real. Bell test experiments are real. And the speed limit for usable information remains intact. The strangeness is not that quantum mechanics lets someone send a message across the universe in an instant. It does not. The strangeness is that entangled particles produce patterns that cannot be explained by ordinary local classical stories, while still refusing to become a cosmic telephone. That refusal matters. If entanglement allowed faster-than-light messages, causality would be in danger. Observers moving relative to one another could disagree about whether a message was sent before it was received. The same paradoxes that haunt faster-than-light travel would return through the quantum door. But the no-communication theorem keeps that door closed. Quantum physics may be strange, but it is not careless. Entanglement shows that the universe is more deeply connected than classical physics imagined. But even here, in one of the most mysterious confirmed phenomena in science, reality's speed limit still holds. The boundary is not broken by quantum weirdness. It is respected in a quieter and more subtle way. The universe allows particles to share a strange kind of togetherness. It does not allow that togetherness to carry a message faster than light. The speed of light is now one of the most familiar numbers in science, but it was not always obvious that light had a measurable speed at all. For much of human history, light seemed instantaneous. A candle was lit and the room brightened. The sun rose and the landscape appeared. Lightning flashed across the sky before thunder arrived, but that mostly showed that sound was slow, not necessarily that light had a speed anyone could measure. Light was so fast on human scales that it seemed to happen all at once, as if vision reached out and the world simply answered. The first convincing evidence that light moved at a finite speed came not from a laboratory, but from the moons of Jupiter. In the 17th century, the Danish astronomer Ole Rømer studied Io, one of Jupiter's largest moons. Io orbits Jupiter regularly, passing into Jupiter's shadow and then emerging again. These disappearances and reappearances could be timed, rather like a distant celestial clock. But Rømer noticed something strange. The timing of Eo's eclipses did not remain perfectly regular when viewed from Earth. Sometimes they appeared a little late, sometimes they appeared a little early. The key was Earth's changing distance from Jupiter. When Earth was moving farther from Jupiter in its orbit around the Sun, light from Io had a longer distance to travel, so the eclipses appeared delayed. When Earth was moving closer, the light had a shorter journey, and the timing shifted the other way. In 1676, Römer concluded that light must take time to cross space. He did not produce the modern value exactly, but he had shown something profound. Light was not instant. It had a speed. That was an enormous conceptual step. The delay was not caused by Io being unreliable, like a tiny moon with poor timekeeping habits. It was caused by the travel time of light itself. The solar system had become a measuring instrument, and Jupiter's moon had quietly revealed that even the fastest messenger in nature does not arrive without a journey. Later, scientists brought the measurement of light down to Earth. In the 19th century, Hippolyte Fizeau made an important laboratory measurement using a rotating toothed wheel. He sent a beam of light through the gaps in the wheel toward a distant mirror. The light reflected back and returned toward the wheel. If the wheel rotated at just the right speed, a tooth would block the returning light instead of allowing it through the original gap. By knowing the distance to the mirror and the rotation rate of the wheel, Fizeau could estimate the speed of light. It was a wonderfully mechanical method, using spinning teeth to measure one of the deepest constants. In physics, science is sometimes elegant, and sometimes it is elegant while looking faintly like a very serious bicycle part. Léon Foucault improved the measurement using rotating mirrors. Instead of relying on a toothed wheel, Foucault used a rapidly spinning mirror to send light toward another mirror and back again. During the tiny time the light spent travelling, the rotating mirror shifted slightly. That small change altered the returning beam's direction, allowing the travel time to be measured with great precision. Foucault's method also helped show that light travels more slowly in water than in air, supporting the wave theory of light over competing particle ideas of the time. These measurements were not just exercises in better numbers. They showed that light speed could be tested, compared, refined, and connected to the physical behavior of waves, optics, and eventually electromagnetism. The speed of a light was becoming less like a mysterious blur and more like a measurable feature of nature. Today, the situation is even more interesting. Scientists no longer measure the speed of light in vacuum in quite the old way, because it is now defined as an exact constant. The meter is defined using the distance light travels in vacuum during a specified fraction of a second. In other words, the speed of light is so central and stable that it helps define the unit of length itself. This international system of measurement is connected with the International Bureau of Weights and Measures, the organization that helps maintain and coordinate global standards for units. The modern definition does not mean scientists stopped measuring reality. It means measurement has been reorganized around constants of nature that can be reproduced with extraordinary precision. Instead of keeping the meter tied to a physical metal bar stored in a vault, modern science ties it to light, time, and atomic precision. This is a quiet but remarkable change. A unit of length, something as ordinary as a meter, is now defined through the behavior of light in vacuum. Distance is connected to time. Time is measured with atomic clocks. Atomic clocks use the stable frequencies associated with transitions in atoms, especially cesium atoms in the definition of the second. The result is a system in which length, time, and light are woven together with astonishing care. Atomic clocks make this possible because they are incredibly stable. They do not measure time by swinging pendulums or turning gears. They measure it through regular quantum behavior inside atoms. That precision feeds into technologies that depend on timing, including satellite navigation, telecommunications, radio astronomy, and tests of fundamental physics. Laser ranging also depends on the speed of light. By sending a laser pulse toward a reflector and measuring how long the light takes to return, scientists can determine distances with great accuracy. This technique has been used to measure the distance to the Moon, with reflectors left there during Apollo missions and robotic lunar missions. Light travels to the Moon, reflects, and returns, allowing the Earth-Moon distance to be tracked with extraordinary precision. Interferometry adds another layer of sensitivity. By comparing light waves and studying how they overlap, scientists can measure tiny differences in distance. Interferometers are used in precision metrology, astronomy, and gravitational wave detection. The same basic idea, comparing the behavior of light along different paths, appears in instruments that can detect changes far smaller than anything human senses could notice. So the speed of light is not only a philosophical boundary, it is practical. It is built into how civilization measures distance, time, motion, and position. It helps define the meter. It helps synchronize systems. It helps spacecraft navigation, satellite timing, laser measurement, astronomy, and precision experiments that test the foundations of physics. The fastest thing in the universe has become one of the anchors of measurement. That is fitting, because the speed of light is not just a number attached to a beam. It is a relationship between space and time. It is the speed of causality, the boundary of influence, and the constant that lets modern physics translate distance into duration with extraordinary precision. Human beings once wondered whether light had a speed at all. Now that speed helps define how the world measures itself, the speed of light is often described as a limit, but it is more than a boundary on motion. It is the universe's causal speed. It defines how quickly one event can influence another. It tells light how fast to cross empty space, but it also tells information, gravity, and physical change how quickly they can move through space-time. It is the difference between events that can touch one another and events that remain, at least for now, beyond each other's reach. This is the deeper meaning hiding behind a familiar phrase. The speed of light is not only about light, it is about reality's ability to update itself from place to place. If something happens here, the rest of the universe does not know instantly. The information must travel. A flash must cross the distance. A gravitational change must ripple outward. A signal must move from one point in space-time to another. The cosmos is not one single instant awareness. It is a vast, patient structure where cause and effect travel at a finite speed. Without that speed limit, the universe would not simply be faster. It could become incoherent. If signals could move instantly, or faster than light in ordinary space-time, then different observers could disagree dangerously about the order of cause and effect. A message might be sent before it is received for one observer, but received before it is sent for another. In some arrangements, faster-than-light communication could allow causal loops, where effects circle back into their own causes. That is not just strange, it threatens the basic order that lets physics describe events consistently. Relativity avoids this by giving space-time a causal structure. Light cones separate what can influence an event from what cannot. Events inside the light cone can be connected by signals moving at light speed or slower. Events outside remain causally separated. This does not make the universe less mysterious. It makes the mystery ordered. It gives reality a grammar. That same rule appears again and again in different areas of physics. In special relativity, Albert Einstein showed that the speed of light in vacuum is the same for all observers in uniform motion. To preserve that constant speed, time and space cannot remain absolute in the old Newtonian sense. Moving clocks tick differently when compared with other frames of reference. Lengths along the direction of motion are measured differently. Simultaneity becomes relative. The speed of light remains fixed while space and time adjust around it. In electromagnetism, James Clerk Maxwell showed that light is an electromagnetic wave, a travelling disturbance in electric and magnetic fields. The speed of light emerges from the behaviour of those fields. That discovery made light speed look less like an accidental property of brightness, and more like a natural constant built into the laws of electricity and magnetism. In general relativity, gravity obeys the same causal limit. Einstein's theory describes gravity as the curvature of space-time, rather than an instant pull across empty distance. Gravitational waves detected by the laser interferometer, Gravitational Wave Observatory, travel at essentially the same speed as light in vacuum. When black holes merge, space-time does not announce the event everywhere at once. The news travels outward as ripples at the speed permitted by causality. In particle physics, the limit appears through energy and momentum. Objects with rest mass can be accelerated closer and closer to light speed, but never all the way to it. The energy required grows without bound. In particle accelerators such as the Large Hadron Collider at the European Organization for Nuclear Research, protons are pushed to speeds extremely close to light speed, yet the final step remains unreachable. Added energy increases their relativistic energy and momentum, while their speed approaches the limit by smaller and smaller amounts. In quantum mechanics, the rule survives even where intuition struggles most. Quantum entanglement allows correlation stronger than classical physics permits, as shown through Bell's theorem and Bell test experiments, including work by Alan Aspect and later researchers. Yet entanglement does not allow usable faster-than-light communication. The no-communication theorem explains why measurement outcomes cannot be controlled to send an instant message. Quantum physics may be deeply non-classical, but it does not turn the universe into a faster-than-light telephone exchange, which is probably wise given how chaotic ordinary phone signal already feels. In cosmology, the speed limit shapes what can be seen and contacted across cosmic time. The observable universe exists because light has had only a finite time to reach us since the hot early universe. The particle horizon marks the limit of what can have sent light to us by now. The cosmic event horizon marks a deeper future boundary in an accelerating universe beyond which some regions may never exchange signals with us, no matter how long time continues. So the speed limit does not make the universe small. In a strange way, it gives the universe scale. It creates horizons. It gives the night sky depth. It turns astronomy into time travel of the most honest kind. Not a machine carrying someone into the past, but ancient light arriving after a long journey. A nearby star is seen as it was years ago. A distant galaxy may be seen as it was billions of years ago. The farther away something is, the older its message usually becomes. This gives distance an emotional weight as well as a scientific one. Stars are not merely far away in space. They are separated from us by the finite speed at which reality can deliver information. The light entering a telescope tonight may have left its galaxy before Earth had complex life, before mammals, before flowers, before the first human looked upward and wondered what those lights were. The universe is not only large, it is delayed, it is layered with old messages still arriving, and yet modern physics is not finished. The speed of light is central to the best theories available, but deep questions remain. Quantum gravity is still unresolved. The black hole information problem still challenges the relationship between general relativity, quantum mechanics, and thermodynamics. The deepest connection between space-time and quantum theory remains uncertain. Some physicists suspect that space-time itself may emerge from more fundamental quantum relationships, though no final theory has been confirmed. That uncertainty does not weaken the speed limit. It shows how important it is. Any deeper theory must explain why causality works so reliably, why light speed appears as a universal boundary, and why mass, energy, fields, and space-time fit together as they do. Reality has a speed limit because space-time, energy, mass, fields, and causality are not separate rules scattered across physics. They are parts of one connected physical order. The universe is understandable because influence cannot go anywhere instantly. Events have relationships. Signals have paths. Horizons have meaning. Time and distance are woven together. Light moves at the fastest speed reality allows, not because it is merely quick, but because it traces the boundary between what can happen together and what must wait. The limit does not close the universe down. It gives the universe its shape. So, why does reality have a speed limit? The calm answer is that the speed of light in vacuum is not only the speed of light, it is the maximum speed of causal influence in space-time. It is the fastest rate at which information, energy, gravity, and physical change can travel from one event to another. It is the boundary that tells the universe what can affect what must wait, and what can never be reached at all. That idea took a long time to become clear. Galileo Galilei helped show that steady motion is relative, and Isaac Newton built a magnificent picture of motion in absolute space and absolute time, where speeds can be added in a straightforward way. James Clerk Maxwell then revealed light as an electromagnetic wave, linking it to electric and magnetic fields. The failed search for the luminiferous ether showed that light did not seem to need a hidden medium after all. Then Albert Einstein's special theory of relativity changed the meaning of space, time, and motion, showing that light speed remains constant while time and distance adjust around it. From there, the same limit appeared everywhere. Time dilation showed that moving clocks tick differently. Length contraction showed that moving distances are measured differently. Mass-energy equivalence revealed why objects with rest mass require more and more energy as they approach light speed. Photons, having no rest mass, travel at light speed in vacuum, while ordinary matter can only approach that boundary. Causality showed why faster-than-light signals would threaten the order of cause and effect. General relativity brought gravity into the same structure, with gravitational waves travelling at the speed of light. Black holes revealed causal boundaries so extreme that even light cannot escape outward from within an event horizon. Even the largest and strangest parts of physics respect this idea in their own way. The expansion of the universe can make distant galaxies recede faster than light, because space itself is stretching, yet local signals still obey the causal limit. Quantum entanglement produces correlations stronger than classical physics allows, but it cannot be used to send messages faster than light. Precision measurement now uses the speed of light to help define the meter itself, tying distance, time, and motion to one of nature's deepest constants. So the limit does not make the universe less mysterious. It makes the mystery more precise. It allows science to describe which events can touch each other, which messages can arrive, which horizons can be crossed, and which regions remain forever beyond reach. The speed of light is not merely a rule for bright things moving through darkness. It is a deep feature of how space, time, energy, mass, and information fit together. And somewhere at this very moment starlight is crossing the dark. It carries ancient information from distant suns and galaxies, moving at the fastest speed reality allows. It is not rushing beyond the rules of the universe. It is tracing the shape of space-time itself,